authenticated or send audio codec.
Yeah,
Oh?
use the audio.
Audio codec. Pick audio codec.
Yeah, it is.
Yes, now. Okay. No more.
I don't know, it shouldn't matter because nobody's speaking into the microphone.
Oh.
Yes. Hello, hello, welcome.
Oh. Yes.
Welcome, hello. Testing 1, 2, 3. 3, 2, 1. That's good.
Yeah.
No.
Okay.
That's all good.
Okay, I'm gonna go inside.
Yeah.
Right. Yeah, sorry everybody for the little delay, but now we're ready. So hello everybody. My name is Tyler Cody. I'm a research assistant professor from the Virginia Tech National Security Institute. I'm also head of the Responsible General Intelligence Lab we have there. And today I'll be talking about some test and evaluation first principles for general learning systems. And I'll get into exactly what I mean by that. But I'm just really happy to be here. I'm really happy that you all chose to attend this. And I want to start with just an observation that if we look across those systems, like, for example, robotics in healthcare, which could greatly improve patient outcomes, or other systems that we dream about, like maybe at a much smaller scale, like robotics inside the body fighting illness, to a much bigger scale, okay, like smart cities that are highly connected, highly optimized, and so forth. Maybe to what I personally think is some of the grandest ambitions of humanity, like in-space assembly and automated space exploration. If we look across all of these, I sort of challenge you on which parts we're missing. I mean, in many ways, we have the materials, we have the electronics, we even have a lot of the sensing systems we need. The mechanical engineering is pretty straightforward. I mean, what's the missing link? There's clearly something about how all those parts come together that's not working. And I think that that missing link is intelligence. I think that most of those grand systems we dream of are actually intelligent systems. And what we need really is a new paradigms for engineering. There's for some reason, we're not able to put these things together in such a way that at the end of the day, they're fully intelligent. And so that's sort of the theme underlying today's workshop, today's tutorial, this concept of new paradigms for engineering and what those might look like. The tutorial is structured in terms of 3 lectures. So the first is on test and evaluation, those practical and pragmatic aspects of test and evaluation. And I really just want to drive home the point that it is tractable. There's a lot of people out there who are quite worried about artificial intelligence and even just testing machine learning and if it's going to be possible. It's very possible. I want to just make sure that's known. The second lecture, I want to get a bit more philosophical and talk about the kind of mathematical structure of learning systems and how that can support systems and test engineering. And as great as that is, by the time I get to the third lecture, I want to show that actually there's limits to that, and that that kind of mathematics is really tied to the current paradigms, and those kind of break down as we start to try to scale the intelligence of our systems. So that's the structure today. And overall, the lectures are structured to be about 45 minutes. So originally those would have ended roughly where the break is for the next workshop. We'll see if we get there. We're starting a little bit late today. And so that extra time in between to do question and answer and really try to get in some interest-led discussion on specific topics as the lectures are a bit more general. And as far as the goals of this tutorial, really, it's to try to provide AI researchers with some understanding of engineering processes, the ways engineers think, and in particular, a lot of the ways that acquisition systems and procurement processes have to deal with engineered systems. And at the same time, to try to provide engineers who already are kind of thinking in those terms, some understanding of the unique aspects and challenges of engineering AI. Overall, I hope this can be a forum for talking about this. And really, I just want to try to share this engineering-oriented perspective on AGI and paths forward towards AGI. So before I get into it, just a little bit about myself. I graduated from the University of Virginia with a PhD in systems engineering. I consider myself to be a systems theorist and machine learning engineer. Day to day, I'm developing and applying systems theory to try to bridge systems engineering and artificial intelligence. And my academic mission is to develop rigorous first principles for engineering AI-heavy systems, where AI-heavy systems are what they sound like. They're systems where the dominant factor in success, the dominant factor in achieving the needed outcomes of that system is the AI factor. And I have a quote here from Capablanca that in order to improve your end game, you must study the end game before everything else. Whereas the endings can be studied and mastered by themselves, the middle and the opening must be studied in relation to the end game. It was a quote about chess and obviously a much broader quote about life, but I think it really undergirds this idea that first principles will tell us where we need to go. I also see it as kind of battle cry for systems engineering, where it's like, let's try to figure out what we actually want to build and why we want to build it before we just start tinkering. So let's look farther out into sort of what are these underlying paradigm of the current engineering and how that might be lacking when we think about where we want intelligent systems to go. Okay, so diving into the first lecture, and here talking about those practical and pragmatic facets of testing, in part so that we can get those out of the way and have more interesting conversations as we go through the tutorial. Basically, at a high level, when we go and do top-down engineering, that gives our goal to our system, which tells us what we should test. Test and evaluation is about informing decision-making. Okay, and when we test, we're gathering evidence. When we're evaluating, we're making judgments on that evidence. And those judgments obviously are to make a decision. As we go through the lecture, I'll use these three takeaways to sort of drive the different points I'm making. And the first is pretty straightforward, right? But it's something that people really haven't accepted in the engineering world, that the properties of AI depend on the system that they're integrated into. And the properties of that system are going to depend on the AI. That's something we can't avoid. And it's actually a positive thing. Second, another positive thing is that as we integrate those learning systems, the tests become more generic and more common to what we've seen before. So we can use a lot of existing methods, processes, and tools for test engineering. Lastly, I just want to drive home this point that it's not just the learning system, but there's a lot of support systems that are needed to keep it up and running. And if we don't also test those, that can be a big problem. It ends up being a benefit, though, because if we're highly uncertain about the environment, we can test those support systems to have confidence at least we can recover when failure does occur. Okay, so the title of this slide says general intelligence is coming. Depending on who I'm talking to, I either say it's here or it's coming. Here, I'll say it's coming because I don't think autonomous vehicles or autonomy necessarily rise to that level of general intelligence. But with this figure, I just want to point out that we're no longer in a world where it's just individual isolated machine learning functions or learning systems doing some kind of narrow task, some kind of auxiliary task. More and more we have dozens dozens of machine learning tasks being solved at the same time, and they're critical. They're critical to the system's success. They're even safety critical. More than that, as you can see here, there's a lot of overlap in what they're making decisions about. And so there's a lot of interactions to test related to how all those machine learning functions come together. And so it's a pressing issue, and that's really motivating this tutorial, but as well the research I'm doing in this area. I think it's also appropriate I define general learning systems and what I mean by that. And I mean a few things all at once. It's purposely vague in a way. On one hand, this tutorial is about general learning systems because I'm talking about those general principles that are going to apply to all learning systems. Even though a lot of testing is going to be domain specific, there are some things we can say at the general level. And so that's what I want to make sure to convey. And I think it's important to do that. On the second level, it's general in the sense that here we have a plot of, say, intelligence versus the number of tasks. And if we measure intelligence in terms of like some complexity weighted sum of the performance across a number of tasks, then it's going to increase up and to the right as we get more tasks. And so you look at something like autonomous vehicles, that has maybe dozens of different kind of narrow AI that we're composing to try to form some more general kind of intelligence. And in a sense, that's a general learning system because we can model it as one single big learning system that's doing lots of different things. Okay, so that's also a kind of general learning system. If we keep going though, and we take this human level marker, human level AGI, maybe that's somewhere after this kind of phase change that occurs, where we can't really just count how many tasks a system is solving. It turns into a problem of, a problem where systems that are that intelligent are deciding what tasks they should solve, right? In fact, they're probably spinning up learning systems to solve new tasks that they encounter. And so I have it as approaching infinity here, just to emphasize that point that it makes sense to sort of say, oh, it's a general learning system because it has lots of tasks. But then at a certain point, it switches from that to it's a general learning system because we don't necessarily know what it's going to be learning in the future. There's high uncertainty with exactly what the inputs will be, exactly what the data is going to be, and so forth. And so in that case, it's general in the sense that we literally can only say a few things at a high level of abstraction about what the kind of learning mechanisms are. Okay. So with that, just get into some background material. As far as the scope of this tutorial, I want to try to draw a divide between a few different branches of research. The first is one we're probably all familiar with, which is AI research, okay, which is heavily oriented towards the optimization formulation of search problems. Like, okay, is it well posed? How do we regularize it? Will it actually converge as we get more data? What are some bounds and kind of guarantees we have for that? Up to say numerical methods and some basics of scientific computing to make sure we can actually compute these things. But then there's a big jump when we move to AI engineering research, which is certainly concerned with scalability and how do we get these things to run in distributed computing systems. That's a big aspect. But then there's these other, say, pillars of AI. People usually refer to these things as pillars of AI, like privacy or trustworthiness or explainability or robustness or fairness, et cetera, et cetera. There's a very long list of these different terms. And of course, they're all commingled and nested, but oftentimes they're put as these individual pillars, and researchers, especially academics, will sort of specialize in a pillar or two, and we'll treat them independently. And that's great. We're learning a lot about those different areas, but we have to be honest that none of those things actually rise to the level of an engineering process, which, if followed, would realize a learning system, would realize an intelligent system that actually meets our needs. And that's what AI systems engineering research is all about. How do we go from a conversation with a stakeholder about what they would like this system to do to actual instructions that go out to all the different components of that system, come back and are integrated and realize a system that can be deployed in the real world and do the kinds of things we want to do. So that whole sequence, it's not just processes, but it's that kind of view. What I'm showing up here is the systems engineering V when I say AI systems research. And that's this general model we have as engineers. It's not necessarily that you have to follow this exact process, but it does describe the basic steps. You'd be hard pressed to try to come up with a step that I couldn't model as being part of this, right? So at the high level, we start with need analysis. We talk with the stakeholders. We figure out what do they want? What do they need? What do they value? And we somehow start to turn that into requirements about the system. Then with that set, we can define the system, and we start this process of decomposing the system and its requirements, first from system to subsystem, and then finally to components. Once we get to the component level and we've decomposed the requirements all the way down to the component level, the job of the systems engineer is basically to farm out all the work to individual disciplines who are often domain specific to say, get the electrical components right, get the computing hardware, the sensing, and so forth. And maybe the machine learning engineering is one of those. And I think in many ways, a lot of learning systems are components of the system. And then we climb back up the systems engineering V, okay, recomposing the components into subsystems and subsystems into systems until we arrive at a fully integrated system. We're ready to do some system level validation, deploy it, and then we're into operations. So from left to right is sort of the idea is going through time here. And so here's a more in-depth view of what it might look like. When we're below, we come up with the idea of the system and we do all this decomposition, and this philosophy is like, if we just figure out what the right components are and the right way to put them together, then we're golden as engineers. And in lecture 3, we'll talk about how that's a limited perspective. But with that in mind, usually everything going on related to requirements is called verification. Did we actually build what we set out to build as far as the requirements we wrote? And then once we get to the full level system, we call that validation, which is, did we actually get the system that we want? Is it going to make the stakeholder happy? Is it going to do what they need them to do? So as far as testing, when we're recomposing the system, this is the first place testing really comes in, and that's called developmental testing, developmental test and evaluation. And the other big branch of testing is called operational test and evaluation, which starts at that full level system. Okay, and the first job of operational test and evaluation is really to say, should I actually buy this thing? And then after that, it's through operations and maintenance, sometimes called sustainment. So there's basic tests to make sure the thing is still operating. It's still the thing I bought and wanted to buy and so forth, all the way up to retirement, which involves testing as well. So just a little bit, putting some words to that. Operational testing is basically conducted on the finished product in an operational environment or representative environment, ideally the actual one, right? Because we want to evaluate everything in the real world context, the real world conditions. So just some words for what that might look like. The user acceptance testing is a big part of that. The basic performance testing, but this can be system level performance, right? Okay, so based on what we want the system to do, not just prediction accuracy. Security testing is really big in operational testing because now we have a full system. We can actually go red team, or we can go. We can basically try to break the thing, right? From a cyber perspective, which often requires having the full system because it's the chaining of vulnerabilities that get that done well. On contrast, developmental testing is happening during development. And a lot of what we normally call testing machine learning, basically cross-validation on a good day, right? If we have the time, that's really developmental testing, okay? Making sure that the learning algorithm is actually converging. If I show it data, it can perform on data similar to it. That's some basic confirmation that the component's working, but it's not actually, let's say, full system level testing if we scope beyond just the individual learning system to the entire system it's integrated within. And that drives us to the first takeaway, which is really simple and pretty straightforward. But the fact is that machine learning and AI, these learning systems that we're interested in building are actually subsystems or components of a bigger system. And we have to realize that things like generalizability, the trust we have in those systems, the robustness of those systems, the properties of AI actually depend on the system that AI operates within. And of course, the converse is true. Designing our system, operating our system is going to be affected by the AI that's within it. Okay, we should be able to do our design in AI with some acknowledgement of what the challenges are going to be for those learning components. Okay, so understanding these relationships is key. So that's the first basic takeaway. Now, getting more into the process, there's this idea of pipelines. I think everyone here has probably heard of pipelines. Pipelines are great in the sense, I mean, they've well treated lots of different things, including data, right? Data pipelines. We have the modeling pipelines, and in a way, software development is turning into a kind of pipeline itself with DevOps and so forth. One of the things here, though, that bothers me a little bit is that testing is totally relegated to these like two little boxes. This is just an example I pulled from the internet, but model evaluation is the extent of developmental testing, right? That cross-validation. As if developmental testing shouldn't also include some basics of how is it going to fit into the workflow where it's going to be? How are users interacting with it? Are they using it the way we think it should use? How does it interact with the sensors and the various controls on that platform where we're going to put it? And so it kind of suggests that we can completely automate a developmental test, which is a bit of a problem. And then the other thing, which I'm glad to see it, and almost everyone acknowledges this monitoring and logging, like we should be detecting something like some basic concept drift in the data and trigger and update our models. But that misses the fact that this is actually a really big decision we're making, okay? Because a lot of times, or I think in a lot of systems at least, when we're using AI, we're willing to put up with that stochastic aspect of it, the data inadequacy of it, and so forth. It's because it actually has a really big effect on what we're doing. It might be the difference between being able to have a capability and not have a capability. So the idea that some little automated trigger that detects some distributional difference is going to take my AI offline is a big problem. Actually, there should be a structured decision process and one in which I can actually pay to buy down the risk. There's actually a sequence of tests, maybe leading up to the fact of asking someone to sign off on the liability of this thing to keep it running if they really want to keep it running. But it's obviously a much more involved thing than just monitoring and logging, right? So this is a problem with pipelines. The other problem is these pipelines tend to act on individual machine learning systems, let's say, but individual models or the model plus the learning algorithm in isolation. Like every different machine learning model is going to have a different pipeline. It's pretty rare we'd have one big pipeline for all our models, but isn't the reason we should be triggering and logging and doing all this stuff because the interaction of those might be going awry? That's kind of an issue. But going back to the previous takeaway, if a lot of if we actually have more than one chance to affect the performance of the machine learning models, of the learning systems, it's not just, oh, we got to build it right, get the algorithm perfect and get the perfect data, but we can actually make decisions about how we're going to use it, about how we design the system around it, then we ought to represent in the pipeline the fact that it's not just a software problem. Okay. Because I bring this up to people and they'll say, okay, well, yeah, we have the ML ops pipeline and then we plug into DevOps. Is that okay? Then it's integrated. Well, is your whole system software? If it is, then okay, maybe that is a large enough framework, but it's probably not all software, right? So that's what they miss. So test and evaluation is a much deeper kind of thing. It's a much deeper topic, is what that says. And the terms on this slide don't matter as much as the overall process. And so let me just step through that to give a sense of what the kind of life cycle looks like from a test perspective. At the beginning of anything with machine learning, right, or anything really, we want to scope what we're going to do. Okay, what's our actual problem we're solving and so forth. In machine learning and learning systems, we got to figure out what's the data we're going to use, how do we integrate that and set those flows up. Then the initial model development. And we have to do all of that before we can do testing, right? We have to just have some baseline model that we can actually start testing, even just the developmental tests at the component level. So during those three phases, it's really important for test engineers to be a part of that process to be able to answer some key questions. For example, am I going to have labels? And if so, when am I going to have them? If I'm not going to have labels, how are you going to manage that risk? Because now when I say labels, I mean ground truth. If you're not going to have ground truth, how do I actually know what the performance is going to be in the real world? There's all these kinds of questions early on to ask. Going back to the machine learning pipelines, and I'll touch on this later, they can also include contractual requirements, like making sure you have access to that pipeline over time. Okay, because if it's a third-party vendor who's providing you your machine learning model, what guarantees do you have that you're gonna, what are the property rights? Can I see them all? Can I see the parameters? Can I see the data and so forth? So these are all questions to answer. And then we get to model T&E, which is kind of straightforward developmental test type of stuff at the beginning, but then builds up. So the term live virtual constructive refers to the idea that we're kind of try to create some aspect of the integrated system, but not the full system to test. And it might not be the real world environment. It could be a virtual environment. It could be a live environment, but it's not the full integrated system. And so this could include things like early human machine teaming or human computer interaction testing. It can also be testing that helps figure out what operational tests do we want to run. Once we have the full system and a real world environment, where is it most important for us to spend our time and our resources? This leads to the systems and technology integration, which really the point here is we got to integrate the whole system and test interactions, but then we also want to integrate with the other processes like the workflow, right? We're expecting this AI, this learning system to do something for us. Start to put it in that workflow and see is it actually doing what we wanted it to do? And then that leads to operational testing, which I described basically, the performance. So depending on your environment, this is a US-centric terms, maybe like operational effectiveness, operational survivability, operational suitability. But anyways, that ultimately leads us to models and sustainment, and there's other things to do. So the point is, if you look at the machine learning pipeline, monitoring, triggering, and model evaluation, I really don't think it inherently has this depth embedded within it. But there's a lot of things to consider. And so that can be daunting, but let's actually just look at a little example of how that works. So here I've listed out the test articles and some types of testing, and then some common applicable design of experiments techniques. Design of experiments, experimental design, and statistics are really what undergird test engineering. So we could treat the training data as a unit or a component. Maybe the learning algorithm is a subsystem because it integrates like the data and a few other parts together. Then we have our full system, and then maybe we call a system of systems is when there's like a human there or some other aspect. So there you see the types of testing that we're doing: basic component level testing up to subsystem testing, integration testing, and so forth. And then finally, operational testing. And some of the techniques as they evolve are pretty straightforward. So on the training data, this is maybe most AI centric, where we're going to sort of characterize maybe some combinatorial coverage, like what are the interactions in the data, what's present, what's not. We can also look at the latent space and various latent space representations to say, like, does this data actually look like where I expect the system to be operating and so forth. Then we get up to the algorithm, and then we're looking more at interactions, say, of components. So when how do I pick the data? So for example, I have a computer vision model, and it's on a plane flying overhead, right? So there's all the data flowing in, but there's other things like the time of day, the altitude, the look angle of the camera, and so forth. Those are things that we can start to we can use those to sample the data and then fill that out to sort of check boxes. What conditions have we seen so far? So that's combinatorial interaction testing and optimal learning. In this idea of like, how do we sample the data to test the learning algorithm? And then from there, by the time we get to the full system, we're back to really straightforward stuff from a test perspective. So factorial designs, response surface designs. We now have a system where those unique aspects of learning still make the system unique, but also at the end of the day, it's still just one big system and there's basic things to test. For example, once we get to operational testing, there's basic human factor stuff that aren't going to change. It's still a human interacting with something non-human, and there's a basic set of things we want to test for that. So here's an example of how you might do one of those operational tests for human factors. The term mission might not be as relevant for everyone here, but you could call that location or the company you're servicing or so forth from a business application. So anyways, we'd have the various missions we're going to be on, and maybe in each mission we're solving a number of tasks, and we can sort of list those out in the test plan. And then there's going to be some operational factors we might care about. And here I've just said stuff really generic, like the tempo or the density. So tempo could be if it's a self-driving thing, you know, are we on the highway, or are we in the city, are we in the country? Density relates to that, like how many vehicles are on the road. And then risks, so some sense of consequence. Have we actually tested this thing in low and high and medium consequence settings and so forth? Once we get all that, it's really simple, right? Test it with the human and AI, and test it without the AI. And so there's basic human factor stuff within subject testing, between subject testing, and so forth. So all said, I think that's a really good thing. Okay, so while the component level tests of machine learning require pretty AI specific and domain specific metrics, on the other hand, as it's integrated and we approach a more and more fully integrated system, the testing becomes more generic, and those existing test methods, processes, and tools can be used. So I think that's really good news. Now, moving beyond that a bit, I want to go back to the pipelines and just say, you know, we've been focused on this sort of input-output aspects. Like this system is this function actually that we can decompose and recompose. It's this input-output function. And that's pretty consistent with training pipelines and so forth. But there's this other side of the story that we have to put it out in the real world, get the data back, has to come back to us, and then we can update and learn. And yes, there's an arc here in the pipeline, but I don't think it really gets into the detail of what that involves. And so here's just a little diagram to try to walk through that story. So we have the training pipeline, and on the other side of that, we have a trained model, which is great. But then we have to put that model into our system. Okay, so for a neural network, we might have to quantize that, or there might be some various hardware differences and so forth that emerge. So we get the model out of the training pipeline, but then we actually have to put it in the system. That's what I'm calling the delivered learning system there at the top. And then we have to actually put that into the real world to do things. Operations is just the idea of like being out in the real world, performing operations with the system. And that's when we actually first get the genuine feedback of, can it actually do the stuff we want it to do? We have to observe that. It doesn't come free. It's not that, it's not necessarily the case that we can always see what outputs it's producing always for what inputs and so forth. We actually have to engineer that into it. And more than that, if we actually want to understand what was the result or the consequence of using a learning system, we have to be monitoring the outcomes as well. Outcomes being like in the game theory sense, just those things that are happening in the environment where we're using the system. So that doesn't come baked in. And then there's these two different feedback loops. The first is the shorter loop. I'm just calling here sort of real-time quality control or near real-time quality control. Maybe at the simplest level, this is your ensemble. Like you detect some minor change in the environment from what you're expecting. You just reweight various models in an ensemble and you update it. It could be a little bit more involved with that. Like maybe there's actually some online learning or transfer learning you're willing to do out on the system at the edge or so forth. But really, and also you can engage other systems, right? Take a system offline. This is one of the big things in responsible AI people talk about is, I shouldn't be sarcastic. People want an off button for AI, right? You got to have that big red off button or something like that. So that's also a decision to make. Are we having unintended consequences or are there unintended behaviors going on and so forth? So that's all in this shorter term loop. The longer term is this re-engineering feedback. And this is something I think is minimized by this machine learning pipeline oriented view, because that re-engineering feedback, maybe at a minimum, it's probably is like gather some different data, rerun and retrain the model. But maybe gathering that data actually requires going through modeling simulation process to generate that data. Or maybe, maybe more than that, we've actually got a better understanding that we should have some new requirements. Okay, we should go all the way back to scoping, and we've learned enough actually that we should go back through an acquisition process. So in a world where the same company owns all these different steps, I think things can flow a lot more smoothly. And you could have metrics like, oh, how quickly can we get through this loop and so forth. That's great. But is that really going to be the common case in the world? Probably not. There's going to be someone who owns the system or owns the asset. There's going to be people who service that. And among the people who service that, there's going to be people who provide models, like model vendors. There's going to be people who provide data. There's going to be people who set up the infrastructure to run all of that. And the point of bringing that up is just to say it's a complex contracting process, okay, an acquisition process, procurement process, whatever terms you want to use to go through that whole thing. So if we have to go back to the training pipeline to get new data and we didn't have that in place for the contract, there's no new data. If we're not paying a company to maintain their pipeline over the years, there's no pipeline to reiterate through. And so actually doing this reengineering can be quite expensive if we don't have some kind of foreknowledge that we'll need it. Now, thinking about needing it, if we look at this just a little bit longer, let's think about some different settings. So, for example, if we're very certain about where we're going to be operating, like either we know it's going to be a very simple thing we can collect data quickly for, or it's a very basic task we can perform very well on and so forth, then we might not anticipate having to go through this loop many times. Maybe we can have this kind of feed forward, like build my model, ship it, and I'll get new requirements later and I'll update a new version of the model later, but I don't need to monitor, I can pay a lot of money up front to do a lot of developmental testing because I have high confidence that the evidence I gather is going to be long lived. I can actually accrue my evidence by running that testing and it will apply to the real world. There's a lot of cases where it's not like that at all. It's like, hey, I want to go use a learning system in your company to do your things. And I know I have no visibility to what that is yet, but I'm confident that I can do it. How do you actually sign off that that's okay and you'll let that happen? Well, the focus of testing has to shift away from that individual component to this bigger process. Can you actually test the ability to do this near real-time quality control? When there's a failure, how quickly do you catch it? Can you update the model? Is there a fallback system? Do you query a human for liability reasons or something like that? And similarly with re-engineering, one of the most simple tests could be what I was sort of alluding to is like, is the contracting set up right so that I could actually retrain this model and so forth. Another common one is data labeling, right? People say, okay, well, I'm collecting data from the real world. Okay, but can you label it? How much data are you collecting? How quickly can you label? Are you willing to pay for that? And how long does that take? So these are different things we can test that feel like they're more on the operational side, but actually they're much easier sort of binary 0-1 tests, or maybe some timing, more than 0-1, but some timing of how long these things take, these basic mechanisms. But it's not as difficult as trying to build a model of the stochastic behavior of some learning system, especially as it gets more intelligent. And so if we don't appreciate this whole process, we can kind of tie our hands behind our back because we say, oh, well, we don't have the data to test it. We don't know what's going to do. It's like, okay, well, test that you can actually iterate. And so that leads to this third and final takeaway for the first lecture, which is there are systems, technologies, and processes that are required for learning over the life cycle. Okay, and they're also defined outside the scope of the training pipeline. Okay, they're often actually easier to test before operation than the learning systems themselves. And so it shouldn't be like, oh, our scope just increased. This is horrible. Actually, it's like, wait a second, maybe there's something way easier to test than the AI that can give people the confidence to buy my AI and let me learn over time and make it better. And so in conclusion, I hope that this gives you a sense that test and evaluation is tractable. I mean, if you start just saying like a learning system and you're worried about, well, the data is always going to be inadequate and it's stochastic, and because of those things, even just our subjective view of what it can do over time is going to be changing and so forth. These are things that traditional components don't have, and they are daunting. But as I've shown today, there is a place to start. So those three takeaways in review is that the AI is part of the system, okay, making sure it can generalize and so forth, can benefit from system design and operation. The second is that as we integrate the learning components more into their systems, the testing becomes more straightforward, okay? Because now we're looking at higher level systems things and very simple requirements about what the stakeholder thinks the system should do. And lastly, the third is that there are these mechanisms outside of the traditional scope of a learning system that are necessary for its success, and we can test that. And often they're easier to test before operation than the actual learning system itself. So, with that, I'd like to shift to questions and answers regarding this lecture and these sort of practicals and pragmatics of testing. Yes, sir. Absolutely. So the question was, can we represent this systems and test engineering process as a problem for AI to solve? And the answer is absolutely yes. So in the second lecture, we'll actually be talking about how to represent learning systems with models that are compatible with the models we use in systems engineering today. And that's sort of the first step to say, how can we represent the learning systems on the same terms that we represent sensors and controllers and so forth. Once you have that, then you actually have a formal representation of the system, and then you can start to optimize. So sort of two different sides of the coin there. The formal methods side of chugging through the logic of do these components fit, is the timings of the interfaces working and so forth. And then there's the more inferential side where we actually have to choose where should we collect data to go get some empirical evidence about this system. But absolutely, and it's definitely an ongoing area of research. And I don't know if they talk about it here at Digital Futures, but there's this field called digital engineering, which is really the revolutionization of engineering towards things like that, where instead of contractors just sending in a piece of paper, like a PDF describing their system, they're actually giving a model that's testable. And then the systems engineer is actually integrating all those models together in an environment over the lifecycle, even during development and so forth. So that's a dream, and sometimes that's called model-based engineering. Great. Yes.
For example, in machine learning, there's the different methods like precision or robustness, and sometimes they are scale off between measurements. For example, higher precision may indicate lower robustness. So if there are levels of active process and multiple process together, how do we balance your scale off maybe among this?
Yeah, thank you. So the question, let me try to repeat it to make sure I've got it, was something like, there are different trade-offs we have in the metrics for machine learning, like precision versus recall and so forth. And also at the same time, we're putting these systems together piece by piece, and there's different levels of testing to do. And so the question is sort of generally, how do we think about that and deal with those trade-offs? Well, at the component level, I mean, I don't have all the answers, right? And I think actually the answers are going to be in the domain application. So sometimes recall matters a lot, other times precision matters a lot, and a lot of times it's about the user. So just some basic examples there. Like in a common example would, a lot of people may have heard of, is like credit card fraud, right? So the false alarms are a really big deal, because if your credit card company is calling you every day, say, oh, maybe there was fraud, and every day you're saying, no, it's not fraud, you're safe, but you're also not happy, and you can probably switch companies. So there's certain domain-specific things where the economics of it or the user interactions or so forth drive where we want the model to make its errors. So that's on the domain-specific side. As we integrate them together, I think that's also a kind of open question. How do we weigh that? I'll give a little story about using a computer vision model where it was supposed to help people identify things in a scene. So you have these, let's call them analysts, looking at their computers, and they're looking at videos passed, and they're supposed to, identify what's going on there. And the computer vision model is pretty good. Like, you just give it the scene and it can do it, that job. But it can't, it has a harder time at, say, video streaming and other stuff. So there's a reason to still have the human in the loop. Well, in one version of this test, the human operator, seasoned expert, all of a sudden starts like zooming in aggressively, zooming out aggressively to build up a model for themselves of what's going on in the scene. And as soon as they start doing that, the machine learning model breaks. So there's a lesson there in that you don't know how the model is going to be used, how the learning system can be used until you actually integrate in the workflow. And in that case, you could find out accuracy doesn't matter at all because, on the normal case, because as soon as we start moving around the pan and the zoom, it just breaks. It gets worse than that, actually, though, because when that started happening, the AI, the bounding boxes it was putting on things started flickering around all over the place. To run a good test, there was an option to turn off the AI. Turned out about 50% of people turned off the AI once it started flickering because it was annoying. So there, accuracy really didn't matter at all, right? Because they just turned it off. Now, those kinds of things you can expect at the beginning of a project, right? As you're learning what actually matters, where is it going to be used, and what matters. As you go on more and more, that stuff becomes settled. You realize, wait a second, my data should include different zooms and pans, and I should be including that in training data. That pretty much gets solved. That's a factor that doesn't matter anymore. If the accuracy gets good enough and the users are trained, it's not going to flicker all the time. They don't turn it off anymore. And so the more we get that integration smooth, the more that the machine learning engineers can have like meaningful data, meaningful factors driving the tests they run at the component level, so that they can have assurance that once we integrate the whole thing, it's actually going to like do stuff we want it to do. Okay, so over the life cycle of the project, we figure out what factors at those different levels of the system matter. We then incorporate that into how we run our tests at the component level. And in that sense, I showed the system engineering V there, but in that sense, what we're actually doing is flattening that V. We're actually not, we're making it so that at the component level, we're almost sort of doing something that looks like operational test, and we can accelerate much quicker. So it's a bigger story than you asked for, but it depends is the answer, certainly. Great. Are there any other questions or comments? No? Cool. Well, we've made up some time, which is great. And so I think I should go ahead and launch into the second lecture, which for me is very, one of my favorite topics, actually. Some of the papers I'll be discussing the results of were published over the last couple of years at this conference. So maybe more on point. And really, it's about an open systems theory of learning systems. So let me not dive too much into it and just start with the point that we can use systems theory as a kind of meta theory for many things, but including learning theory and machine learning. And that affords us the ability to top-down design and operate and test systems with their learning components. Okay. Now I just use the word top-down, and in many ways, a lot of approaches to AGI are kind of bottom up, right? We build this algorithm that can come to be able to do many different things. But what I'm saying is that we can sort of top-down decide that we want to do that, okay, as opposed to just tinkering and hoping. The idea is that if we're just going bottom up, we're planting all these seeds, something might bloom one day, but we don't really know what's going to bloom. Okay. So when a stakeholder wants to buy an intelligent system to do something, they don't really want to hear that. So it helps answer that question. Now, there's 3 takeaways. The first is pretty straightforward, but it's that we can actually just prove to you we can formalize these things in a reasonable way, and that those models are then stratified. So we can look at the learning systems at different levels of abstraction. The second gets a bit more into the operational use, and the idea that the structure and behavior and concepts of transferability can be used to relate those challenges faced by the learning components all the way up to the system level. So we can actually have some intuition. Oh, if I actually choose to operate this way, is that going to make it harder or easier for some learning subcomponents? And then the third takeaway, which is more of a summative point, is that the model of learning systems we provide actually are a general kind of category, a category of general systems. Therefore, when we define some requirements for these kind of general models, they'll apply to a lot of different solution methods. So that's something you'll understand more what I mean by there as we get in. So again, the scope. When we think about the systems engineering part, going to the comment from the last section, the question from the last session is, how do we actually make this a whole integrated process? How do we connect the systems engineering work to the actual machine learning work. And I chose to go about this through general systems theory, which I had a colleague once tell me that general systems theory is simultaneously the most interesting and most useless mathematical theory. There's a quote from one of the founding fathers about its conception, which is, there exist models, principles, and laws that apply to generalized systems or their subclasses, irrespective of their particular kind, the nature of their component elements, and the relationships of forces between them. It seems legitimate to ask for a theory not of systems of a more or less special kind, but of universal principles applying to systems in general. So this kind of school of thought led to what I call a descriptive general systems theory, because despite its aims, it didn't actually formalize itself much. Around the same time, cybernetics was being developed. So we're talking 30s, 40s, 50s. By the time we get to the 40s and 50s, we actually have recurring conferences on this stuff. And there, cybernetics can be kind of thought of as a general systems theory of control. And it showed that we can actually apply formalism to general systems and arrive at very useful conclusions. And so perhaps inspired by that, mathematical general systems theories were formed. And two of the big ones in those early days were that of Masarovich, termed abstract systems theory, and that of Wymore, which really evolved into what's now known as model-based systems engineering. We'll be using Masarovich's model. The main difference between these two is that whereas Masarovich stays more formal and builds up towards category theory, Wymore, well, he has his own conception of the engineering process, and in order to fit his models to that, basically you have to make a lot of assumptions, discretize the system objects and so forth. And the focus of Wymore's work becomes about the interfaces between components and the timings, and how can we just make sure that all is going to work out. Now, I've just trivialized this work, but I don't mean to. It's just to say that the other work is more formal and more general, and that's what I build on. And the philosophy here is quite simple. So I maybe should have said this earlier, but this question of what is a system, sometimes people get really, they don't want to answer that question, right? Oh, what's a system? It depends what a system is. I don't really think that way. I think that the system is clearly the whole formed by parts and their interrelationship. Okay, so parts, they come together, they have some relationship with each other, and they form a whole. That's the system. And so there's no difference between that and the formal representation of that, which is that a system is a relation on component sets or system objects. So that's this whole idea, is that the system is a relation on component sets. So we got to figure out what those component objects are and then figure out the relationship between them, and we will have defined the system. And the idea here, and this gets to my joke about this theory being a bit useless, is you have to know why, how, and why to use it. The motivation was that we want to go from a block diagram to a formal representation with sort of a minimal loss of generality, which might seem crazy, right? But actually it's quite useful. So in the engineering process, we often have, or modeling process more generally, we have a verbal description, we then create some kind of flow chart, some kind of block diagram of how everything's related. And then after that, it's very tempting to jump down to a detailed model, even if that detailed model is just some basic algebraic equations, right? So for example, in a lot of mechanical systems, as soon as we figure out the basic block diagram of the system, we jump down into basic state space equations in terms of the number of joints and so forth. We've actually stepped over this whole phase of modeling formally the block diagram. And once we do that, if we do that, we can then add detail as we go. So in the case of machine learning, we can add some learning theory and we can work our way out towards the machine learning solution methods. And this is really important because as systems engineers and test engineers, we're interested in that abstract system that we're building with a particular solution method. We're not driving towards a particular solution method. That'll become more evident as I talk through this. You can't really talk about systems theory without justifying yourself, I think, in many ways, because it has been around for a while and it doesn't have too much to show for it. But its early applications were more towards biological systems. And the fact is that abstract systems theory, general systems theory, it's at something like the 30,000 foot level. And by the time we add enough detail to properly represent a biological system, we're basically back at the ground floor. I mean, we have to add so much detail that it's no longer a general system. We might as well have just started talking about the biological system in the first place. In contrast, machine learning and learning theory are similarly general to general systems theory in that they're after these general processes for general learning problems and so forth. Actually, we can see that theoretically. So abstract systems theory is largely a theory of sets, and learning theory is often a theory of probability, or in other words, measures on those sets. And to get to machine learning, we just often add a bit of algebra to get the optimization formulation more well-defined than in a lot of learning theory. So in that way, mathematically, these things are very close. And so that should give you some intuition that they're useful. The second point gets back to this engineering problem and the focus of systems theory on systems and not problems. If you read enough machine learning papers, you'll sort of sense that most people there focus on this problem-solving formulation. Like this whole idea of domains and tasks. We're learning a task in a given domain, so we're sort of like the problem is to do well on this task, and the setting is the domain. The problem, there's not a huge deal with that, but it is different to talk about solving a problem versus a system that comes to be able to solve a problem, or a system that can solve problems. Consider if I define a system as a relation on sets, it seems to specify something about what a system is. But if I say a problem is a relation on sets, it doesn't seem like I specified anything about the problem, right? So they're happening at different levels of abstraction. The point of wanting to have this systems theoretic viewpoint is that it makes those principal concerns of systems and test engineers primary. Whereas if we have the problems lens, we at least have to translate out to the systems. And so it's at least a secondary topic. But going back to my scoping, it's also tertiary in many ways, because what people consider secondary is like, how do we get this thing on distributed computing? That's AI engineering. And so it's better just to start rooted in systems. So there's this difference between domains and tasks and systems. And then the language that follows ends up being different, right? Even if the mathematics is compatible, it's important what we say first, because it constrains everything we say after that. And when we talk about systems, we get the much more natural language of structure and behavior. Okay, structure is like, I mean, it varies, but usually more like, in the case of domains and tasks, the structure would be, say, the input set and the output set, whereas the behavior is those probability distributions defined over those. And so domain and task muddle this distinction between structure and behavior, which may not be a problem for problem solving, but for system integration, when every other system component we think about in terms of structure and behavior, that can be a difficulty. Okay, so with that, I think I'm motivated to provide enough motivation and background. So let's go into formalization. This was presented a couple of years ago at this conference, but it's pretty straightforward. At a high level, systems are taking in data so that at some point later, they can take in inputs and give outputs. So at a high level, they're really not any different than an input-output system, which is kind of like all systems, right? Many systems, if not all systems, are input-output in some respect. At a deeper level, they're really this cascade connection of two systems, a learning algorithm, which takes in that data to pick parameters, and then some parameterized hypotheses, which can take in inputs at one point to give inputs at another point, outputs at another point. Essentially, what I'm modeling learning as function approximation, which isn't the only model for learning, but it's definitely the mainstream conceptualization today, and it's what a lot of statistical learning theory is based on. And then if we go a level deeper, I would say we should add detail to the algorithm. And that's where we realize the search process itself actually isn't this input-output process, but you have some kind of goal or objective, and that's giving values to something. And then you have the search process, which is taking those values and picking parameters. And so the inputs of one are the outputs of the other, and so forth. And actually, it forms this kind of closed subsystem. Okay, these kind of consistency relations, which can't necessarily be isolated. I mean, clearly we're missing an independent variable between the two. And so when people talk about the black box side of machine learning or AI, I mean, on one hand, okay, it's black box because the data writes and the software writes and so forth, but also it's fundamentally black box because the search process itself. So here are some terms to that. And I promise it was a whole PhD actually to think exactly which terms should we consider first and in what order. This is the art of doing systems modeling. But once we have this top-down model, it can be quite useful. So just to drive home some common sense of how we start modeling with this, let's consider an unmanned aerial system that we want to do path planning for. So in this case, the inputs are going to be the sensor readings, right? Okay, GPS, radar, the cameras, maybe some other stuff. And the outputs are going to be the flight paths. Where do I fly? Let's be really naive here and say we're going to do supervised learning. So give me pairs of flight paths and sensor data, and I'll just somehow learn what that function is. I say naive here because in reality, we probably want to use a model of the platform and have some basic physics understanding of the flight paths. But just for the sake of modeling here, we can say, okay, we're going to have labeled data, essentially. Okay, so that's the first level. Let's go a level deeper. let's say we want to use support vector machines. Okay, so in that case, we're saying what the algorithm is going to be. Well, then, of course, we're making assumption about the hypothesis space, right? That it's going to be half spaces. And and if we want to follow canon, when we go to the next stage, lower level down, we'll use hinge loss for the loss function, and we can optimize that with a linear program if we formulate it right. So there you go. I've just specified a system that we can then compare to everything else, right? I could have models of where's that sensor data going. I could have models of where's that flight path going, and you start to get that sense. So you can do a similar thing with learning theory. So, I mean, machine learning theory. So just some common sense stuff. I find this helps clarify what I mean by data. So in supervised learning, right, we have labeled data. So it's input output pairs. In unsupervised learning, we don't. Okay, we just have input data. There's the difference in a sense, depending how you want to define these things. Empirical risk minimization is a statistical learning theory, one of the earliest and most basic with lots of results. Anyways, it's a little bit more detailed where now it doesn't have to be input output pairs, but I've just said it's input output pairs. But we make this assumption that it's independent, identically distributed. Okay, we're learning from an unknown distribution, but we can sample from it. That's the first basis. And then the second part is that we're using an empirical measure of risk. What that exactly means, you have to open up the learning theory to see, but it's just a high level constraint on what the objective functions can be. And then simply we want to minimize that empirical measure of risk. So you can start to get a sense of that. And if we take that to the extreme, we can get some pretty cool things. So here's that stratification, the input output level, then the second level and the third. And I've called these the elementary level because often we call elementary systems or just input output systems. The cascade level because there's the cascade of the learning algorithm into that hypothesis space. And then the goal seeking level because we include that closed subsystem that makes everything a little bit more tricky. So we've got that, and then just project that onto learning theory, and we can start to look at what metrics should we be testing for, getting to your question about precision and recall. So at the highest level, at that basic input output level, we can already start looking at things like the monotonicity of inputs and outputs, the basic information complexity, basic questions about distribution. These are pretty important things when we want to decide what algorithms are going to be appropriate. Going a level deeper, really things start to unlock once we know what the hypothesis space is going to be. We can start to actually answer questions about what's the capacity of that hypothesis space, how flexible is it when we change the parameters and so forth. How much does the function change? Oh, what's the sample complexity in a sense, if we can draw from the data and the distribution as well. And actually the funny thing is, in a way it's funny, you don't actually get to error until you get down to the goal seeking level, and error in the sense of the loss function or the, that term within the objective function. And so your instinct when you say, oh, I want to build a learning system, and one of the first things you might think of how I'm going to measure the error. Actually, that's a pretty specific thing, and you're going to measure it differently based on the particular solution method you want to use, right? So for example, if I'm doing some kind of domain adaptation, I'm probably going to need a distributional divergence term in my loss function. I think this underscores the difference between concept of error at the input output level, which is going to be more related to, say, precision and recall, which has downstream effects on the integration, versus the concept of error that's actually driving the learning process. These things can be different. And so that's the vision. So getting to the question of how do we do systems engineering for all this kind of stuff, we have these input output models of all the other systems. And now the question is, how do we have input output model of learning? Well, because of the stratification, we can add low, so that input output level, like just taking in data and inputs, so the elementary level, we can consider that as modeling with a high uncertainty for what the actual solution method is going to be. If I can write down my requirements for my system at that level, that's actually great for me as a systems engineer, because then I only have to test at that level. And also I give the machine learning engineer or the AI engineer all the space in the world to figure out how they want to solve it. Okay. If I go a step deeper, I start to specify things, right? I probably need to specify there's a learning algorithm to truly be talking about a learning system. But do I really need to specify what the loss function is going to be? I don't want to say absolutely not, but almost absolutely not. And so we can sort of top down descend into solution methods without knowing exactly what that solution is going to be. And that's really important when we start to have conversations about AGI, right? Because in many ways, the AGI is not going to be defined for a particular task, as we were talking about, right? And so if I want to use this kind of theory to try to model an AGI I'm seeing, I can do that at this highest level, like look at the tasks I've seen it solve and start to tease out what its capabilities are. I don't have to start at a detailed model. I don't have to say, oh, they're using the NARS system. And so therefore, I need to model these specific components. It's like, no. At the end of the day, NARS is just input output, and we can break down all the way from the input output level to that level of detailed solution method. The more I learn about what the solution method is, the more I can build up my model of it, but it's not necessary to start a engineering process, certainly. And I almost don't want to go down to that level of detail for an engineering process. So that's our first takeaway, is that we can model these things formally and at multiple levels of abstraction. Okay, so this is an explicit link between all these broader bodies of systems research, which talk about input-output systems and deal with input-output systems, and that of learning theory and machine learning. Okay, so let's turn to transfer learning now, which is really fundamental, right? Transfer learning is just the case when we have some particular target setting we want to do learning in, and we want to borrow knowledge from some other setting that's not that target setting, to put it simply. Okay, we usually call it the source and the target. When we think of it in the problems terms, we say, oh, there's a source domain and a source task, and a target domain and a target task, and then we sort of reason about, oh, are the domains equal or the tasks equal, how similar are they, and so forth. Well, if we represent the source and the target as a learning system, then we can represent transfer learning as a relation on that. And so in a sense, the transfer learning connects two learning systems by sharing knowledge from one of those systems to the other. And I've defined it in a pretty general way here as the power set of the data and the parameters, just to say, which is pretty much convention, right? We're either going to share the data to train the model or the parameters of that model, something like that. You could extend it, it doesn't really matter. The point is, transfer learning basically has this additional input of knowledge. We can model that as data. And once we do that, one takeaway, and I don't know, I could go do a whole lecture on this, but one takeaway is we can start to specify these things in a more formal way than the traditional literature lets us do. So in the table there, I'm describing those basic approaches of transferring data. People call that instance transfer, transferring parameters, parameter transfer. I know intuitively for mathematicians, yes, it is just a function from the target data and source data to the parameters and so forth. But we ought to acknowledge that, okay? And as systems engineer, I might say, hey, that's the one I want. Don't tell me any more about what you're going to do, other than the fact that I'm going to make sure you can get these two datas, and then you're going to give me parameters, something like that. Some key results in there relate to transferability defined in terms of systems. And the way I try to back into this with the question of how many systems can we transfer to and generalize, and a separate question of how many systems can we transfer from and generalize. So one system, maybe it can be used in a lot of different settings. That would be like a very general system. Then there's also an idea of a very general setting, where like almost any model can perform well in that setting. So these are two different questions, and we can start to model them in terms of neighborhoods of systems. So in systems theory, we talk about stability like this, and right? Okay, stability around a point given some error function. Well, if we have some threshold on error, we can just say the transferability of a source is the number of targets we can transfer to, given that the error in that target is less than some threshold. And we can do something similar for the target. So this gives us a general sense of like how can we talk about this stuff, but also maybe this is something we should engineer for. Now, this leads to the formalization of transfer distance. Transfer distance is informally used by a lot of people, right? Oh, this is near transfer, this is far transfer, to indicate these two tasks are similar or dissimilar. For example, near transfer would be like, I have a self-driving car in one city, and I want to bring it to another city, and both cities are very similar, same make and models of cars and so forth. That's near transfer. Far transfer would be like, I taught this car how to drive, now I want it to go compose a piece of music for me or something, right? So actually, it's a statement on this distributional divergence, or the sort of general differences between two systems, behavioral difference between two systems. And this is why you'll see across machine learning in the loss functions, we'll have all these different distributional divergences to handle this kind of stuff. So we could have F divergences, which includes the KL divergence, Wasserstein distances, kernel-based methods, and so forth. And it all draws from domain adaptation theory. And I've completely, I mean, this is a conceptual inequality. It's not real, but it gets at the general idea. In domain adaptation theory, you'll see that the error in the target is upper bounded by a combination of the error in the source, the distributional divergence between the source and the target, really the divergence between the inputs, and then some other term people often use to try to get a tighter bound. Okay, that could be the capacity, it could be some information complexity, and so forth. And what this tells us, the main takeaway is that, as a lot of us already know, but as systems engineers should definitely know, that these distance metrics are fundamental to transferability, and therefore to the way that these systems fail. Okay, so that's behavioral similarity. What about structural similarity? I should note that, right, if you just saw a lot of machine learning and read a lot of learning theory, you would get to domain adaptation theory eventually and then realize divergences have this fundamental place. But because I started at systems and then I said, okay, behavior, and then I said behavioral similarity, it just came out naturally. It's one of the first things you would consider. And same thing for structural similarity. In this case, I'm talking about, I define it as roughness, and something about the structural homomorphism between two systems. It doesn't, homomorphism just means like the similarity of form. It doesn't matter too much. I don't want to go into too much depth other than to say that it's a lot worse of a metric, just because if two systems are isomorphic, great. Okay, so I mean, there is a sense of minimal roughness. These two systems are structurally the same, but if they're structurally different, there's not really this idea of maximum roughness. I mean, what does it mean to be structurally different? Is it just that the input, you know, the mapping from one system to another system's onto? Okay, that's great. Well, if it's not onto, then how, what part of the sample space is not able to be mapped onto the other system, and so on and so forth. So roughness is important to consider, but it's not everything. An example of roughness would be the difference in sensor systems, for example. Is it the exact same sensor system or is it different? In which case, if it's different, then I might need to value, well, okay, do I just not have a dedicated vibration sensor, but I can get that from the accelerometer? So if I approximate it, then I can actually recover some structural similarity and so forth. So you can use these kinds of concepts to reason about engineering process. And I want to step through a little notional example to do that. So let's imagine we have two flying things, two unmanned aerial systems, one of them solid body, one of them hollow body. Okay, hollow body, so that's a structural difference in the system, obviously, but it's also a structural difference in the data, because we know from mechanics that basically the more degrees of freedom a body has, the more degrees of freedom its dissipation will have, the vibration signal will have. Okay, and so there's a structural difference in the data there that, it's at the system level, it's also at the data level. And then let's imagine a behavioral difference, like inclement weather. Okay, is it raining or not? That's a behavioral difference, right? Same system, same structure, different behavior. And that'll also change the data too. Let's just assume if we're looking at something like vibration data, then when we have weather there, it's going to be a higher amplitude. Because it's there's more going on. Let's just say, I'm just notionally. So all that's to say, we can sort of think about structure and behavior, and then think to ourselves, like, how difficult is it to transfer across these differences? If I started with domains and tasks, I don't think it would be as easy to reason through this. Okay, so the takeaway there is that structure and behavior relate the generalization capability through transfer and roughness to system design and operation. So that at the beginning, I was saying we can think about design and operation with consideration for those component learning systems. If I choose to now use this machine learning model in a completely new setting, but there's a really high distributional difference, then I've just made that life of that learning system a lot harder. So it's my choice that's changed how well it's performing. I do mind if we take a break. I prepared everyone in the room that we started late and such. I appreciate the thing. Yeah, we will be after this lecture, there'll be a chance to switch, I guess, if you'd like to. But anyways, I'll continue. So this is all building, and so we have transfer learning here. Cool. Two systems transferring knowledge with each other. They can both transfer knowledge with each other. And if we do that, then it looks something like multitask learning, right? I mean, that would be figure A there. We have one algorithm that has a bunch of different hypotheses space it's responsible for. That's a little bit different than meta learning, right? Where we kind of think of meta learning as a kind of learning system for the algorithm itself. And so these are just basic kinds of composition. Normally in systems theory, we think of composition as like series, parallel, or feedback. But actually, for learning systems, which are richer, we can define a new set of compositions, such as transfer learning, multitask learning, meta learning. And these things are related. So here, what I'm showing is that bidirectional transfer learning is actually a kind of, structurally speaking, is a kind of multitask learning. Okay. Interesting, and it kind of matters in a sense because when I say, "Hey, build me a learning, build me a transfer learning system," they come back with a multitask learning system. Is that okay or not? I would say it's totally fine. Now let's take that to an extreme. So here I'm just going to step through a variety of transformations. On the top plane, I have that bidirectional transfer learning system. Okay, so it takes some data that goes to the algorithm that feeds parameters to the hypotheses, and that's going on twice, and they're sharing the knowledge with each other. On the lower plane, I'm representing each of those has a meta learning system. Okay, so let's start doing some transformations here, structurally speaking. So the first thing I can do is combine those algorithms, turn that top plane into multitask like we did before. So that's what's going on from A to B. Now from B to C, what I can do is actually the same procedure, but to the meta learning algorithms. So now both those meta learning algorithms are acting on an aspect of the algorithm on the top plane. From C to D, I can collapse those hypotheses spaces. I think you can see where I'm going with this, and so forth. And I have to, in E, I'm kind of showing how I'm redefining stuff internally, but the end of the story is we get back here at F to the learning system. So because these things were defined appropriately, actually that definition of a learning system is a very general category for which transfer learning, multitask learning, meta learning, and I'm sure a variety of others can be applied. Therefore, if we define requirements on this system, those requirements will also apply to transfer learning solutions, multitask learning solutions, and so forth for this particular system. So as a systems and test engineer, it's really great to know, hey, look, as long as I'm respecting this formulation, then the requirements I'm defining, the measures I'm coming up with will apply regardless of the solution method people are bringing to me. Which brings us to our third takeaway, that there's this kind of general category of learning systems that's defined here, and that supports this solution method agnostic engineering. So as you can see, what we're doing here is building a lattice work of first principles. The idea isn't that this systems theory alone can solve all of our problems, but it's a coherent logical structure, okay, that lets us relate all these different aspects of learning theory, all these different aspects of machine learning to each other. Therefore, when we're faced with a new problem, we can sort of traverse through the systems theory, figure out where in the space of learning theory and machine learning we should look, right? And then dive into the specifics. So to just stretch the metaphor, the systems theory is kind of the lattice work, and then going into learning theory and machine learning is like growing out into those open spaces. I don't know exactly how to do transfer learning just because I know systems theory, but I might know I need transfer learning. Okay, so I realize there's some loss of synchrony with the other tutorials, but I do want to go through this example here because I think it drives home the point about lifecycle engineering for a learning system. So imagine we have a bunch of actuators. Okay, actuators just create some kind of movement in a physical object, and we want to have learning systems to predict when they're going to break. That way we can optimize our maintenance, save costs, have lower inventory, and so forth. Well, the machine learning approach to solving this problem is like, how can we use the same model on all these different actuators, even though they're slightly different, is going to be right to statistically relate the source and the target, use some combination of selecting and weighing the data or transforming the data and so forth. Okay, great. That's important. That's important. But if we have this system scoping, maybe we can actually just understand and design the actual cyber physical nature, if you will, of the distributional change. In other words, because I'm building the system, because I'm designing the maintenance procedures, I can control how hard the transfer learning problem is. And it's quite important in this kind of example. Consider that when a machine fails, we have to rebuild it, and then it's a kind of different machine. And so if I'm trying to collect failure cases, well, each failure case I collect is actually on a machine that no longer exists because I just rebuilt it and it's a new one. So if I can't rebuild my system to control the distributional change, there's perpetually a lack of labeled data. So I can't really do supervised learning unless I can do that. And so with actuator, we actually did this. We had a hydraulic actuator, we added a bunch of sensors, we collected data, And then we deconstruct and rebuilt the actuator, recollected data. So we're simulating a variety of failure modes in different aspects of this actuator. Connecting it to a factory, the idea is that you're pulling data from some production line that's represented here with the circles and squares. That's going to the machine learning model, that's informing some maintenance team, and then they're going and changing that machine line. And we're going to build up to talking about that. But first, let's focus on the actuators. So it kind of seems like a transferability problem, right? So let's take the learning systems and think about this. Well, it's either what I said, it's a new system at each point in time, or it's the same system, but it's sensitive to time. Whatever it is, maybe we can treat it this way. And so that's what I did. I modeled the input distributions, and I took some prior probabilities, and then I did the whole Bayes theorem thing so I could get models of posterior distributions, and then calculated the difference. Essentially, that what I'm doing there is calculating the difference in the learning problem. Now, I'm not saying that that I would do that kind of Bayesian thing to actually solve it, right? I'm actually going to, we use a different kind of model, like a random forest or something, to actually make those predictions. But for the sake of trying to figure out how hard is that transfer learning problem, it works pretty well. So in the table, it's showing the Hellinger distances, which are bounded from 0 to 1, where 1 is the distributions don't overlap at all, and 0 is they completely overlap. And then I'm varying the prior probability. The main point there is that there is some difference, and you can kind of see it, like there's still two distributions. Those distributions correspond to the clockwise and counterclockwise rotations, but their peaks are slightly different. It gets more interesting though, because we didn't just have a binary failure. We emulated specific kinds of failure. And so then I can go across those different kinds of failure and see how much did the distribution change. So if you look at the bypass valve for the likelihood distribution, it was at 0.18 difference. So that's pretty similar on a relative basis. But the leak valve was like 0.74. Those distributions did not look similar at all. And so as a machine learning engineer, you're like, well, okay, I got to relearn or something. Let's collect some more bypass valve failure data. That's going to be a tough. As an engineer, I'm like, those are both valve failures. What causes them to be so different? Is it something wrong with that valve? Like, that's a red flag. So you can see that, it's totally different. So here's some other failures. Look in the posterior of those, which had a 0.8 difference. It's like totally different. The blue is the original data from the original actuator. The red is the actuator after we rebuilt it. Doesn't stop there though, okay? Because what I really care about as an engineer isn't just what the accuracy is. I care about what the downtime is too. So when I have to do transfer learning, my question is, how long do I have to wait before the distributional difference between the data stabilizes? So that if I do transfer learning, I can just do it once. Okay, I don't have to do transfer learning every 10 new samples I get. That's pretty expensive, especially if I have a test engineering process going along with that. Well, what I'm showing in the top left diagram here is a empirical distribution function for a single sensor. And when you can sort of see, the colors aren't aligned well, but basically it's stabilizing as we go up. And what's shown here in the bottom plot is various transfer distances between the input distributions, that's the marginal, the likelihood, which is the input conditioned on the binary health state, and then the posterior. And you can see them going down over time as I get a larger sample, but really around 300 or so, it seems like the transfer distance is stabilized. So maybe at that point, I can say, okay, if we have 300 samples, then do transfer learning, we'll be good to go. Even if it doesn't do well, at least collecting more data probably wouldn't help too much. And then I can back out to say, well, how long does it take to collect those, right? Because usually I'm windowing sensor data. So maybe I turn 5 minutes into 1 point. So 300, that's 1,500 minutes. That's actually a while. So you can start to see how you can get to the engineering problem. All that's to say, clearly we can use transfer distance to link the system design to the generalization difficulty of learning subsystems. And actually just a little story, I don't have data on this, but we did find out it came down to the tensions of the fasteners. So when we rebuilt the system, we just didn't measure the screws basically in the exact tightness of them, which changed the vibration signals, which affected the model. Vibration signals are very useful in predicting when machines are going to fail. So in that case, I either need to have some kind of transfer learning algorithm, which only has an example of like one class per source system or something like that, right? Pretty difficult, might have to wait a few years at least to get that. Or I just give the technician an extra tool so he can measure the tensions and make sure that's uniform. One of those is a lot cheaper. Okay, so now trying to move towards the whole systems level thing, let's consider this production system. We can model production systems, way they're modeled today is pretty rudimentary, but like a Bernoulli process with the probability of the machine is up. Okay, so that's the sort of failures, or is it up? And if it's up, then it's producing parts at a certain rate. And then in between machines is just a buffer. So that could be like a cart to push things around a factory. It could be a conveyor belt. It doesn't really matter. They're all just buffers that have some kind of capacity to store items. So the insight here that I was looking at is that the false positives from machine learning are actually adding to the downtime. Okay, so this is a kind of worst case setting. Also, machine learning should be making things more efficient. But in the kind of worst case analysis, the more false positives I have, the more downtime I have that I shouldn't have had if I didn't use machine learning in the first place. So I pulled some false positive rates from earlier work I did on this actuator. So the original model, or perfect model, let's just say, never has false positive, right? Their model in the lab before the rebuild, basically perfect, basically just memorize everything, right? And then the post rebuild with some transfer learning, and those are two different transfer learning methods, it still had a pretty high positive rate. Honestly, the accuracy was like 80% or so. And so I can plug that in and then get the new probabilities of uptime. So in this case, what I did was I had 5 machines, and I'll have a diagram which makes this more clear. 5 machines, they each have their own uptime. And I said, we're going to use machine learning on the middle one, which had a 0.95 uptime. Okay. And so what that does is just bring that down when we have our failures. You can get a sense of where this is headed, but before the rebuild, basically the same. After the rebuild, not really the same. And so here's some of the results. So we ran this through a simulator. So the circles are the machines with the uptime inside, and the squares are the buffers with the capacity, in between them, how many parts they can hold. It was that middle circle that had the machine learning model. So what you can see in the perfect model, what's underscored with the brackets is where the bottlenecks in the production system are. So a machine that can't produce any more parts because its buffer is full, or because the one before it is empty. When we go from the perfect to the pre-rebuild model, that bottleneck doesn't change. But when we go to the post-rebuild models, it does. And actually, depending on the transfer learning solution method, the bottleneck is appearing in different parts of the line. Okay. Yeah, different parts of the line, right? Same buffer, but the machine is changing where the bottleneck is. Now, why does that matter? Well, as a production systems engineer, I'm constantly worried about trying to reduce bottlenecks. So apparently, actually, where the bottleneck is going to occur depends on the machine learning model. So I might spend a whole bunch of money for the first case because that's what I was designed for in the first. But then as soon as the machine learning genius comes in, adds his model, it sort of ruined everything I did. So that could be a costly error. But that's not even the worst of it. Actually, if we run these simulations for long enough, we can get the steady state throughputs, and it's pretty dramatic. Okay, so that perfect rebuild model is what it is. The one with a slight error, it was going to take 3,300 minutes before we even had 1 part difference in production. But the transfer learning methods, even though they recovered accuracy, say from 50% up to like 80%, 85%, now every 11 minutes, we're 1 part off the perfect model. Okay, that's not 1 order of magnitude, that's 2 orders of magnitude. Okay, so that just goes to show this transfer distance thing actually matters a lot in terms of the system outcomes. In this case, when I say outcome, I'm talking about the production throughput. So all these things should be engineered together. And really it brings up this point, actually, that starts to poke holes in our open systems theory of learning, right? Because what did we do wrong? We took this system, we decomposed it, we figured out exactly how to build it, we put it back together, integrated it, we went through all of that. What was wrong there? What was wrong is the scoping, okay? So some change happened in the machine, which changed the flow, the distribution of the data going to the AI, which made his errors worse, which are going to flow through and break the whole thing. So by being successful, by successfully predicting that we need to maintain this thing, it destroyed itself. That's, I think that's more common than we'd like to admit, is that the machine learning models that are integrated with the world, they can change their environment in such a way that renders them broken because they change the distribution of data flowing back to them. This is a key issue that we'll consider in the next lecture. But in summary, there is good news. Okay, we have this mathematical structure. We can hang lots of stuff off of it. We can integrate with larger systems models. And we have these 3 different takeaways. First, that we can define these systems formally and stratify them. Second, this idea of transferability as a key metric for doing this reasoning. But really, that's just an example. Okay, we could do a similar kind of reasoning with capacity or flexibility or other metrics. And then ultimately, all of these things kind of form a general category. So we can be confident if we design our engineering process around a general learning system, as the particular solution methods change over time, or as different vendors come to us with different solutions, we know that those requirements, those tests, and so forth that we define will apply to them in some way. And that concludes this second lecture. So thank you. I'd like to open the floor to questions. Yes, sir.
More simple structure, what the limits of the more limit. The second question, as a humans, we also like a source of errors, and when we become compose problems, we can introduce some errors into design of the system. And for example, in computer chip design, what design is already being funded by because the text of the system already do not have human computation, and we cannot get any variable gains of the performance as a team if we continue to design the system. What do you think the recent advances in basic models and transform basic but it looks like those systems have a property of general format we can as a basic step everything the recent advancements in this area help us to design better
Great questions. So just to summarize them more briefly, the first question was on the limits of decomposition. And then this idea of categories and category theory might be useful at the general level, but does that really extend as we add more detail? And the second question was a bit broader, but I think the general point was, what about the limits of decomposition and the errors that we introduce as we try to come up with more detailed models without expressing them in the same mathematics as the solution methods? And tagged onto that was, how does that relate to this current sort of set of approaches like transformers and so forth that seem to have general capabilities? So on the first question regarding the category, yes. Well, I think for a lot of the systems reasoning, category theory is pretty good. However, it only tells us very general things, right? So I'd actually, I don't know, personal opinion, maybe category theory isn't very great for specific solution methods at like a detailed level. But perhaps though, perhaps, and this gets to kind of the engineering approach to AGI, we have these more specific solution methods at a lower level like transformers and so forth. Simultaneously, we have other kinds of algorithms working with category theory, looking at the systems overall. And it's those things working together maybe that can take some of those advantages of category theory and its generality and its elegance in a way, without like throwing away algebra, detailed algebra. Now, regarding the errors that are introduced as you're decomposing, that can be a really big issue, which I think actually motivates this work more than takes away from it, because we can sort of choose at any point to say, we're not going to go any further because we're not sure what this is going to look like. We're not sure what it's going to look like. We might know something about what the inputs are. Hopefully we know what the inputs are, but maybe we don't. Maybe we know it's like sensor data, but we don't know what sensors it's going to be. And then, I'm going to have multiple, say, UAV platforms. They all have different sensors. And so I need to be flexible across those. And so until I know the platform, I don't know the specific sensor. But if I choose not to model that, I can still start to do some engineering work. And so being able to model with uncertainty is actually doesn't come when we have very detailed models, like in terms of transformers. If you say, okay, I'm going to build this thing, it's going to be a transformer, let me start writing down the math of transformers, all of a sudden there's going to be a lot of questions you can't answer maybe. Or the things you can answer are so general that it doesn't tell you much about a particular system. I think the question really is, we inch away from input-output system to more detailed model of the learning system, and then eventually we have to jump. And that jump really comes in my mind when we start adding algebra and adding the optimization formulation, because if you have all that systems theory and you're specifying the relation between components, and in that relation is an optimization problem, then then why not just talk in terms of optimization theory or something like that? There's definitely issues there, and that's known. And actually, that's in many reasons why model-based engineering hasn't taken off. I mean, having documents that are vague can be a benefit when specificity itself either can lead to massive mistakes because we assume it's the right thing when it's not, or it just slows everything down because we just start listing out thousands of requirements on everything or something like that. So that's definitely a challenge. I can't myself speak too much to as far as like where the deep learning solution methods are going, but I will make a comment that you take something like the large language models, which are sort of trained just on a general question and answer task. On one hand, a test for that could be something like the Turing test. Does it seem like it's a real person or something for that general question and answer task? If I'm someone buying that so that I can say, read in a bunch of receipts for my company and make sure that those get processed automatically, I don't really care about the Turing test. I care about that specific function I'm buying it to do. So that loops back to this whole engineering thing. If like we have a goal of a system we want to build, if we can keep that in mind, then at least the tests themselves can be defined at that general level, independent of the solutions. So better and better language models might be able to read my receipts better and better, and then I'm really happy. Now that's not really a revolutionary change, right? The idea is like, then the person realizes, oh, it's really good at receipts. Maybe it's good at taking notes for meetings. Maybe it's good. And then all of a sudden they integrate AI in more and more and more parts of their system. And that's where we'll get to in lecture 3, is talking about, is there a switch we need to do where we're not just top-down modeling things anymore, but we're thinking more vaguely about the relationships that are forming over time between different objects in the system, different objects in the environment, and so forth. Thank you. Yes. Yes. Yeah. So the question was, it's easy to show, we talked about transfer roughness. It's easy to show systems are isomorphic because we're just saying, hey, they're the same. But is it easy? How can we actually show that they're different, and how do we think about that process? Well, let me answer that first by talking about distance, because we're talking about function approximation, right? So distance is pretty straightforward between two functions, right? It's actually, it can give us a partial order, like pretty easily, right? So if this one approximation is here and this other one is there, then we just calculate the distance between them. We know they're different. With roughness, we don't have that, right? Because we're not talking about the actual behavior of the function approximation. We're talking about the input-output structure or some other structure of the function. And so fundamentally, it's not as useful because we're doing function approximation, not because some general property of behaviors and structures. Now, thinking about which structural changes matter, I think that maybe there's some interesting mathematical, like pure mathematics to discuss there. But on a practical side, I think because, okay, anyways, homomorphism, one definition of homomorphism is there's an onto map from one system to another system. Okay, meaning the other system could be smaller, but I can map onto it. Well, if it's not onto, this is what I'm saying, if it's not onto, which part actually matters that it's not onto? Like if I'm missing something that doesn't actually matter, does it actually matter to the structural difference? I don't really know. So the ability to relate structural differences to performance is kind of tenuous unless it's really basic stuff like, hey, if you don't have an accelerometer, this thing won't work, 0 or 1. But then we start to think about, like I was saying earlier, well, maybe I have a vibration sensor, but I can get that from the accelerometer data. So I can logically reason, okay, there is some roughness of transfer here, but they're pretty similar. So unfortunately, it's a very philosophical thing that tells us, hey, we should think about this question. But I don't know if the mathematics guides us to exactly what the right answer is without at least the models of what that structure is and how changes in that structure matter. Yeah. Yes. Great. So the question is, we've talked about supervised learning, unsupervised learning, a lot of different kinds of learning, and they all kind of fit in this unified structure we proposed. But is that really the most general? How much more general can we get it? And how does that relate to this pursuit of AGI? Well, so first off, you talk about category. First, start with a bit of a category error, which is most approaches to AGI, learning is an aspect. It's an important mechanism, but say like any approach that's taking cognitive architecture, it's going to have other bits, right? How do we manage the memory or the knowledge and do those kind of processes? So, so this learning as function approximation is appropriate to model that particular mechanism within the larger cognitive architecture. Now, whether or not like modeling the memory is that hard, I don't think the memory might be that hard. Modeling the reasoning systems at a general level might be a little bit hard, but no. So for AGI, I think we combine this learning mechanism with other general systems formulations of the other mechanisms if we wanted to have a general systems theory of cognitive architectures. Regarding learning, I don't think you can prove to me that what I presented isn't representing learning as function approximation. So, so function approximation in the sense of there's literally a function from X to Y that I'm going to learn by looking at data and then create an approximation for that true function, which I can't see. So that's what I've represented at that cascade level. So even reinforcement learning is going to fit there, right? So there the inputs are states and the outputs are actions, and maybe you say the inputs are reward, but maybe that's only coming at training time. So it's in the data that has states, actions, and rewards all together, and the true histories and stuff like that. So maybe in conversation you can try to find a version of learning that doesn't fit that model, but I think it's surprisingly general. Yes. Great question. So the question was, what are the open questions on the table, say that we could approach within the next 3 to 5 years with this stuff? Well, what's the point of research? Is the pure theory. Like I started with that joke. General systems theory is simultaneously the most interesting and useless theory. I'm still out to prove that it's useful beyond just telling this good narrative about how transfer learning in a factory works or something like that. And I think that utility is going to come from the model-based engineering, actually putting this into model-based stuff. So this stuff, I think this community wouldn't be as interested in because it's a little bit dry. But if I have a model of a system, I can automatically generate some requirements. For example, like it has to be able to receive this data, or it has to be handled like this kind of latency or this kind of variability between inputs. Those are basic requirements on interfaces I can derive automatically. So that kind of stuff I think is a little bit straightforward. On the pure mathematics side, I'm interested in, I don't know, I just feel like this stuff kind of unfolds, so it's not that, okay, formally define the category and prove some more category theoretic properties. And then we can view requirements on systems as like contracts on that system. So then we can say, from a requirements perspective, this learning system is good if it's like meeting these contractual requirements, which are just like constraints or some kind of constraint on the sets or something like that. What I think is most interesting to me personally, and what we'll talk about next, is what we can call closed systems theory. So this is really the open systems theory of learning. But what about the closed systems theory? The fact that we're actually putting this open system in an environment and it's interacting with the other system. And just as a teaser for that, so that maybe you come back after we take a short break, but the closed systems, in many ways, it's actually just two input-output systems connected to each other. And so historically, people have said, well, then closed system is a special case of input-output system or open system. Let's just do all our research on open systems because then it'll apply to closed systems. And that's sort of where we are today. But the reality is, if the first thing we say about our system is that it has inputs and outputs, that's different than if we say the first thing about our system is that it has a closed boundary for which there are no inputs or outputs. And so the starting point's different. And so then the arguments end up being different, even if fundamentally, since, it's a special case, it has to be related. So that's kind of difficult thing to deal with. But this question of like what things are in the environment are relevant at a given point in time and so forth, we'll dive into shortly. Okay. So that concludes the second lecture, and okay, let everyone have a break before I dive into the next one. So thank you. Welcome back, everybody. About to get started in a few minutes here on the final lecture of the day about the limitations of everything we've discussed earlier. Great. Well, we'll go ahead and get started here. In this third lecture, we'll be addressing limitations related to closure. And really starts with just try to motivate this where we're coming from in this lecture. I just want to note that engineering methods are centered around traditional notions of decomposition and recomposition to allow for component level properties to hold after composition. In artificial intelligence, however, systems are often expected to influence their environments and by way of their environment to influence themselves. Thus, it's unclear if AI systems can be treated as traditional components. And so what we'll be considering is exactly the limitations there and driving towards some idea about what could those new precepts, alternatives to decomposition and recomposition be. Great. So that's the summary, and there'll be a few takeaways as well. I'll go ahead and mention the first is this distinction between this open systems worldview that's focused on outputs and a closed systems worldview that's focused on outcomes. The second is a more nuanced point that intelligence, as it scales, has a tendency to dissolve the system boundaries. And this can be quite difficult for systems and test engineering to deal with. The third point has to do with exactly what those new precepts are called, corn periphery, and I'll leave that for later in the lecture. So I want to start by this quote from Dr. Pei Wang in his paper on defining artificial intelligence, and he says that since each function he's talking about AI fragmentation, and he says since each function can be specified in isolation, there's little motivation to take the other functions into consideration, as this will complicate the situation. This has important practical consequences, as revealed by the attempts of building integrated AI systems, where component development is crucial, but connecting the components is more crucial. And he notes that this is since the difficulties are mainly theoretical, not technical. I really like this quote because we are in a world where connecting the components isn't just a question of getting the interfaces right. It's a kind of semantic composition. There's truly a meaning behind composing systems and getting them to do what we want. Now here he was talking about the fact that a lot of AI have different assumptions, and when they try to work with each other, they have different assumptions going into that. But I think it also applies to systems engineering, that in engineering intelligence systems, the main challenges we have are theoretical, not necessarily technical. Shown here is the most extreme open systems worldview, just an input-output systems floating in free space. That's just what it is. That's the scope of our engineering. If we go a step further, though, really maybe more accurately representing the open systems worldview is that, yes, we have that open system that we're concerned with, but it's in some kind of sea of other open systems that it's going to interact with. And at some point in time, these two input-output systems will connect, and that sequence will create some kind of functionality. And that all exists within a context. Okay, so there's a first idea of closure there, which is something like, well, the universe is a closed system. There's a bunch of open systems floating around inside of it. And when they interact together, that's what it realizes more complex functionality. Now, stepping more towards closure, the next thing we can note is like, well, actually, there's not just systems out there that take our outputs as inputs and produce our inputs, but actually we can just sort of say, well, from our point of view, those are all modeled together. There's something out there which is taking what we're doing and taking our outputs and then generating our inputs. And we go a step further, we can connect them, and now it's starting to look like reinforcement learning. But that dashed line is still around the system. And what I'm trying to say there is that from the engine, if we're taking this as our engineering model, it's still an input-output system at the end of the day. That is different than if we expand the system boundary to include those other systems it interacts with and say that, hey, at the highest level of abstraction, our open system is actually a closed system of some sort. So these are the two extremes. It's intellectually, it's kind of a spectrum. Mathematically, as I said earlier, the closed system is a special case of open system where we compose two input-output systems together to create the closed system. However, intellectually, it's a different starting point. Okay, and I want to be really clear about that. Okay, because people hear closed systems, they're like, oh, feedback. Well, in feedback systems, at the highest level of abstraction, it's still an input-output system, right? It just has some kind of feedback composition to affect its inputs or something like that. There's another kind of closed system people talk about, which is the one I presented earlier, which is that closed subsystem for goal seeking, the kind of search problem where the goal we have and the way we search for it are coupled, and so we can't necessarily decouple them. That's an important kind of closed system, but that's a closed subsystem, let's say, within an overall input-output system. What I'm talking about here is this really extreme view that the outputs are the inputs, essentially, that at the highest level of abstraction, it's not an input-output system, but it's a closed system with input-output systems within it. And that might seem pedantic, but we'll be building over the course of this lecture. Okay, so now in any time we're trying to go about engineering, we have to make some kind of assumption about the nature of intelligence. Okay, and there's ongoing research into defining this. Some people say that it's measured by integrating complexity, some kind of complexity weighted measure over all the tasks it's performing. Other people say it has to do with minimization in the complexity of state dynamics. Other people might say, oh, it has something to do with adversarial sequence prediction, et cetera, et cetera. There's so many different ways to define intelligence. And I do think this is one of the more general, from Dr. Wong, that intelligence is the capacity of an information processing system to adapt to its environment while operating with insufficient knowledge and resources. So this idea of adaptation under constraints is very general. However, I'm going to avoid the constraining effect of defining a particular notion of intelligence, but instead focus on its nature as a property. So here we say it's the capacity of an information processing system. So it's a property of a system to be intelligent. And then the question is, well, it's exactly that. Is it a property of the system? Or is it more adequately put as the property of the relation between a system and its environment? And now I think, there's a biological question, there's a reality theory question here, that both of which I want to avoid. I'm talking about from the engineering perspective. Do we think it's a property of a system? Because if it is, then it stands to reason that in isolation, in a vacuum, if I could just decompose the system the right way into the right functional components and then recompose them, integrate them correctly the right way into the right integrated system, then it could be intelligent. And while that might be fine intellectually, I think practically there's a huge flaw there, right? I mean, in actuality, it's the way that the system interacts with and involves the environment and itself through that relationship. So this intelligence as a property of the system follows that traditional systems engineering view. And the concept of operations is that we go through this engineering V, we wait until we need to do it again, and then we do it again and so forth. Every time our focus is scoped to that input-output system. In contrast, if we treat intelligence as a property of the environment, a relationship between the environment and the system, then it's more of a continuous concept of operations, where now any part of the system that has a significant relationship with the environment is the subject of engineering intelligence. And that's what's represented by this spiraling dependencies here. It's really that across all levels of abstraction, there's something to say about that relation. Now, you might not be following or believe that that's a reasonable thing to say, but for that reason, I want to talk about deep neural networks for a second, because like many other systems, they're remarkably general. Their requirements are nearly the same everywhere. There's some variations in architectures and so forth, but for the most part, it's this general job of just passing information from layer to layer in a way that follows some basic, mathematical properties like matrix multiplication and so forth. There's variations in architecture, sure, but overall, one could imagine we could write what those general requirements are, and it would apply across the vast number of systems where we use deep neural networks. And so those are requirements on the input-output system. If I were to treat those as all I had, how could I possibly get all the different outcomes in all the different applications I intend for deep neural networks? Clearly, there's something more than just the requirements for that component. There's something more there. Now, people will say, oh, yeah, there's data. We got to fold in the data. And that's exactly the point, is that data is coming from the environment in some way and changing the behavior of the thing. It's more than just requirements engineering of the component. But it goes beyond that, really. So that leads to the first takeaway, which is pretty simple, but it's this point that if we take this open systems worldview, we're focused on the outputs first and the outcomes of the system, like what it actually is doing in the environment second. Whereas if we take this closed system worldview, where we just scope, around the environment and the system itself, then we're thinking about outcomes first, and then asking second, which input-output relationships are generating that. Okay, so this is the first takeaway and our first divergence from mainstream thought in the engineering world. Now, all of that, it really begs the question, what are we to do? Okay, what are we to do if we can't rely on functional decomposition and recomposition as precepts? Okay, first, we've got to admit that we cannot readily specify the needs and outcomes of stakeholders into low-level requirements. Then, with a renewed focus on outcomes, okay, a renewed focus on outcomes, we must turn to some new precepts that aren't reliant on all these system boundaries and persistent system boundaries. So for that, we turn to outcomes, and general systems theory has considered this before. Actually, there's a work called The Law of Requisite Variety by Ashby, which was considering basic problems in control, but really considering homeostasis. How can a biological system maintain the same state over time, despite the complexity of its changing environment? So in this model, we basically have some kind of system, and it's interacting with the environment, and it's a regulator of the environment in a way. It has some of the inputs to that environment coming from the system. Also, we're going to use the idea of variety, which Ashby was using Shannon entropy in his case. And in this case, outcomes are just thinking in the game theory sense of a payoff table. So there's some inputs that the intelligent system can provide to the environment. There's some inputs it gets from some other system, and not this intelligent regulator. And those result in some kind of outcomes, this set Z. So the point of the requisite variety, what leads to is it says that for one system to be a stable regulator of another, the variety of the regulator's output must be greater than or equal to the variety of the regulated system's input. Okay. And so if we put that formally, it's saying that the minimum variety of outcomes is the maximum of the difference in variety between those environmental inputs and the regulator's inputs and zero. So in other words, okay, put more simply, a system can only regulate as much complexity as it can transduce. Okay, so this is important. And what this tells us, it's not that it's the most powerful theory in the world, but it does give us some kind of foundational understanding of how outcomes can be regulated in an environment. If you're moving from this input-output world to an outcome world, then we're looking more at bounding the variety of outcomes as opposed to picking particular outcomes. And so building up towards some precepts, we really want to talk about the change over time in a system and the variety in that. And so first we can just talk about the residual change over time in the inputs and outputs. And that leads us to this idea of a core and periphery, where the core is the stable part of the system. The part of the system that's not that it's not changing over time. And the periphery is the part that is. Pretty simple, right? But with core and periphery, maybe can serve, as I'll argue, as an alternative to decomposition and recomposition. Okay, it's not as clean. We're not breaking everything down to a bunch of functions we can write, isolated requirements for. But it is a kind of coarser disambiguation of which parts of the system are responsible for handling the complexities of the environment, and how are those being used. And so for that, I want to go into a little bit of discussion on exactly how that might play out. And so there are these different concepts I want to explore. So the first is symmetry, and then blocking and abstraction dependence, and then dynamics. So regarding symmetry, consider that the environment has a core and a periphery. So inequalities can be used to compare the relative balance of core and periphery in the system and environment. So that's what's being shown in this matrix here. So in the upper right cases, the system is more periphery dominant than the environment. Okay, in the diagonal cases, there's a relative balance. And in the lower left cases, the system is more core dominant than the environment. Okay, so this is a useful exposition of the general regime we might be in. Okay, so for example, given that given that the system is a regulator of the environment, it's useful to know if a homeostatic environment is being regulated with a similarly homeostatic system, or if a largely unstable environment is being regulated with a homeostatic system, and so forth. However, this doesn't actually. It's pretty hard to assign a relative value to these various cases because symmetry alone doesn't make a statement regarding these variety of outcomes that we're going to be seeing. So this brings us to blocking. So outcome-based value judgments on the distribution of variety across the core and periphery can be made by utilizing the law of recursive variety to consider what the system is demonstrating between the 2 points in time where we're doing our analysis. Okay. Specifically regarding its mechanisms to block the varieties in the environment, in other words, decrease that lower bound so it can actually regulate outcomes. So for example, is the variety in the environment's periphery being treated with the system's periphery or the system's core? We can't know generally, but we can deduce given conditions on the variety. So if the system is a stable regulator of the environment and the variety of a core of the environment is greater than the variety of core of the system, then we can deduce that the system must be partially addressing the variety in the environment's core with the variety in the system's periphery. We have one question, sure. Great. So the comment was from psychology that Piaget had commented intelligence is really in the mechanisms that are in the system. Well, oh, sure. So Piaget says intelligence is the mechanism. Great. That brings back to my point about decomposing the system in a vacuum. If you told me you have an intelligence mechanism, but you've never put it in the environment, I think we have a foundational issue. But this goes back to what I was saying. This isn't a biological theory or reality theory or psychology theory. It's talking about the pragmatics of engineering. And regarding that point, it is true that the mechanisms should fall into the core. So if we were to take a bunch of brain scans and use this kind of core and periphery analysis, the basic functions of the brain should turn up as being persistent across time, whereas the exact way that the neurons are firing as that changes over time would indicate the periphery. And actually, what's quite interesting, and I'm actually leading to this in dynamics, so I guess I'm front running myself a little bit by saying how those things are changing over time can tell a whole story for us. Which system objects are moving from the periphery to the core and from the core to the periphery. So first, a word on the abstraction independence, because you might say, oh, how do we even possibly start with this modeling problem to assess the core and periphery? Well, we might only care about a subsystem. And, if we just want to know if the subsystem is in the core or periphery, in theory, we could just compare to the core and periphery of the whole system. Say, oh, is it in the core or is it in the periphery? But we might find that really hard to do or model as a whole. But since the subsystem is a system, it has its own core and periphery. And therefore, the use of core and periphery doesn't require observability of the entire system. And moreover, by considering the way that the core and periphery is distributed across the subsystems, it can be used to compare the interaction of subsystems within a system without making strong assumptions about the independence of them. Okay. In many ways, when we aggregate our components, we sort of make these independent assumptions so that the requirements at the component level still hold at the system level, for example. Okay. So furthermore, it follows that modeling the core and periphery at the system, subsystem, and component levels of abstraction can identify how the core and periphery are distributed across the system. And when combined with similar stratified models of the environment's core and periphery, it provides this abstraction independent means of modeling the relationship between the system and environment. So we still consider the decomposition of the system, the different levels it might have, but the question is which ones are really peripheral, which ones are constant, and so forth. Now, getting to dynamics, we can model these over time, and as such, the membership of the elements can be traced as they move between the core and periphery. So this provides a natural means of tracing the adaptation in the system. Instead of facing the difficult task of comparing the self-similarity of components, subsystems, and their interrelations at different points in time to see like what evolved and what didn't, we can simply demarcate the varying presence of this residual complexity over time, okay, by looking at the periphery and the core. So for example, if a large change occurs between 2 points in time in the environment, does the system change in response? Okay, was the change in the environment regulated by the system? Meaning, was the variety 0 from that period? Is there some evidence of the system absorbing those new varieties into its core and periphery and so forth? And so core and periphery, intellectually at least, offer a lot of flexibility as far as modeling goes. So this is a little bit more nuanced point. It's quite difficult to make, but if you think about it, if we define intelligence as, in a sense, the ability to regulate outcomes, then as intelligence scales, the complexity of the system has to scale, or the complexity of its outputs has to scale. And so as a result, it's very natural to think that over time, the intelligence system as a whole will use other systems as a way of controlling the variety. In a way, we can think about DNA kind of like this, right? DNA is this very stable thing we have as humans that ought not to change, right? If it starts to mutate, we often have really big problems. And so there's a natural question of given our wildly varying environments over time, how does our DNA just not mutating all the time? And it's because we have these buffers within us. We have our immune system that's fighting off diseases which might threaten to change our DNA, and we have our gut biome, the bacteria that live inside of us, which are even a first line of defense before our immune system has to work really hard, in a simplified view of it. And so you have to take the systems view. It's really hard to draw the boundary just around the intelligent component. What might just start as a machine learning model or something like that, it can grow as the other parts of the system reorganize to support its success. And as it becomes more intelligent, actually using its environment to its own ends, we can say that it starts to influence those systems outside of its original context. And therefore, unless we have this perspective that engineering intelligence is engineering the relationship between the system and environment, we lack the scope to fundamentally engineer intelligence itself. A funny little point for that it comes from this example. And now it's not too intelligent, but it's surprisingly already has this kind of phenomenon. These little vacuum robots people have in their house, these little circular robots that drive around. Reality is, I got one. I was like, oh, great, I don't have to vacuum anymore. Reality is, if I don't, change my house around, if I don't pick up my clothes, for example, it's not going to work, right? It can't move the clothes itself. So the engineer is faced with either like adding an arm to the Roomba so that it can also clean the room as it goes around vacuuming, or it somehow has to influence a change in its environment. So actually, literally, when we were buying our next couch, we decided to buy one that was a little bit elevated so that the Roomba could drive beneath it. And similarly, pick up the clothes more and so forth. So it's funny, to think, I would like to think I changed my behavior so that the vacuum could work, but it might be the case that actually the vacuum influenced me to change its behavior. Needless to say, the engineers are obviously considering that broader scope when they make this decision. And so foundationally, decomposition and recomposition can't do that. It's something more like this core and periphery. Yes, in the front first and in the back. Yeah. So the question was that the phrasing here, transduce complexity, and it's really a callback to the requisite variety. What does that mean? It's pretty straightforward. It's just saying that there's a bunch of complexity in the environment, right? And if we want to control what's happening in the environment, we have to be able to match it with our own complexity, in a sense, to sort of block it out and get to that small set of outcomes we actually care about. And so regardless, so it is about transmitting through the system. It just has to be able to pass through that complexity to the environment. Yes, in the back. Great. So the comment was just for the audience. The comment was basically, or again, regarding Piaget and his theories on the development of intelligence, in that similar to this, it's not about this homeostasis, but actually something he termed homeoresis, which is about this sort of spiraling interconnections between the intelligence system and its environment, which grow its complexity, but also change over time. And so I imagine he probably talks about the concept of self changing over time and exactly where you root it. And that's where this drives to. In the previous lecture, we talked about how those machine failures, the machine was able to predict when a failure occurred. Then the maintenance team went out, repaired the machine, and now the machine changed and the model is not predicting well anymore. The intelligence of the machine learning model is dependent on the way the technicians were actually screwing down all the fasteners, replacing the sensors, and so forth. And so in that sense, intelligence can't just be that individual machine learning model. Now, actually, have some comments on what we're actually talking about here. Just try to, again, there's another angle. In a sense, what we're doing here with the core and periphery is trying to bring some causal, or if that word offends you, which maybe it should, some otherwise statistical or kind of informational plane to the picture, trying to bring those dependencies into the conversation. Okay, this sort of statistical dependencies between the functional components. Whereas this decomposition and recomposition is narrowly focused on the functional aspects of interdependency on this individual plane. And so that narrow view of tradition is expressed by the narrow interest on interfaces and their timings as the primary discourse on composition. Core and periphery, alternatively, allow for discourse regarding how different steps in the systems engineering process, different aspects of test and evaluation, and so on, vary in importance over time. We're not just functionally linking systems together during integration. In artificial intelligence, we're doing this kind of semantic composition of systems and environments. And so as an intelligent system learns and reasons, to the previous comment, its core and periphery will change as it intertwines with the environment, okay, as it composes itself with the environment. So for example, in cognitive architectures, this is a very simple example, but I should mention that in cognitive architectures, oftentimes there's this aspect for managing memory, and the knowledge is going to be reorganized so that the memory that's most important is prioritized for the context at hand. Okay, so that's just a basic example of the core restructuring itself based on the environment. And so as that happens, what we're looking at here is, so what I've represented here in the core is like very high dependency with certain elements at a given point in time. And the periphery is maybe this lower, more longer ranging dependency. And putting them together, I think it just asks these questions, like, where is actually the system boundary, okay, for the intelligence system? What part of the system is actually responsible for the intelligence? Just where is the intelligence of it? So I don't think we can answer those questions very easily. Now, this is about testing, and so I want to try to relate this core and periphery concept to testing. So now we've already noted that the aspects of a system that are in the core are more stable. And while the aspects of a system that are in the periphery are highly bound to change. And so that's one thing, but asking what membership structure is desirable, what do we actually want in the core and periphery at a point in time and over the life cycle is important to answer. And so to some extent, since the core is stable for a given period, it's the part of the system best suited for formal methods, for well-elaborated requirements, and for long-term investment of resources. Okay, testing the core involves testing something that's not changing over time. And so therefore, the evidence is long-lived, it can be accrued, and it can be used over time to make assurance cases and other kinds of guarantees about the intelligence. To some extent, on the alternative, since the periphery is unstable and changing over a given period, it's the part of the system where we need to be thinking less about formal methods and assurance cases and more about risk management and risk-oriented perspectives. So the unstable and changing environments are known to be difficult to test because of the constant inadequacy of data, right? The data, we never have best data that actually represents the current setting. And also the inability of test and evaluation itself, those processes and people, right? To actually keep up with the pace of change in the environment. So therefore, in those periphery dominant aspects of a system, relating engineering efforts ought to be more agile, okay? Also, they ought to have a higher velocity so that they can keep up the capacity of the engineering enterprise for adapting to the incoming complexity. In other words, the engineering enterprise itself becomes part of the intelligence system in one way to buffer that complexity. Tests of the periphery ought to focus on those support systems, like the resilience mechanisms and these feedback mechanisms we talked about earlier that are required to adapt, and have much less of a focus on the statistical performance of component models. For example, really so once we have a model that's good enough and we can ship it out into the real world, we know that performance is going to be changing, the models can be changing. Let's not focus on testing that. As we said earlier, let's focus on testing those things that allow it to change. Allow it to change in a risk managed way, more importantly. Now, focusing on this idea of support systems for a moment, I just want to talk about these resilience mechanisms. So note that successfully operating the periphery involves these core mechanisms that function as support systems for the adaptation processes. So naturally then, when we think about the test budget, when the environment is very stable and the information and the data is stable, then there's not much change, there's not much change moment to moment, and the system is dominated by stable core phenomena. In this case, a heavy budget can be allocated to developmental tests, okay, because essentially we have a high confidence of what things will look like in the future. In contrast, if the environment's unknown, if it's unstable, or if it's otherwise changing, if the data is therefore changing, and especially in the early iterations of an endeavor, the model ought to be thought as in the periphery. And therefore, model test results have a really short lifespan and have and a heavy focus on model testing is likely misplaced. The resources they ought to be optimized to support the operational testing, okay, during operations, between operations, and be optimized for, as I mentioned previously, supporting that velocity of the engineering process, the agility of the engineering process. So as such, it stands to reason that the focus of systems and test engineers ought to be different over time, and the technologies and processes needed to support the engineering enterprise will change over time. In contrast to tradition, the change over time is not that of a simple sequential pass through the systems engineering V. No, it's we're not just we're not doing that. It's actually a flattening of this V in a sense, where it's about strategically revisiting different phases over time. As I mentioned, when things are very core, we're more developmental. When things are very periphery, we're very operational at testing. And so this is not necessarily because we expect to learn and improve over time in a monotonic fashion, like we're always going to be getting better. It's actually the opposite. It's because of the downside. We want to be responsive to those, let's say, information events in the environment, which challenge the learning components to engage. And really what they're doing there is encouraging churn in the core of the system. Okay, it's fundamental. This is going to be fundamental in open world applications of AI, since the complexity of the environment will outweigh whatever complexity the AI itself is capable of. Okay, so that's all to say that if an AI's adaptation is tied to the engineering enterprise, in the face of varying environmental pressures to adapt, it's important that the engineering enterprise itself can adapt so they can direct the dynamics of the core and periphery, and in fact, keep the adaptation process stable. Now, how to do this, I don't think anyone really knows how to do this, but it is a reframing of the issues that I think is an important first step. Okay, this concept of core and periphery, even just in the discussion, it's already been able to provide us with important scope for discourse on ideas that are otherwise pretty difficult to have. That thing of saying will also apply for discourse on engineering processes and so forth. Okay. So, in essence, the philosophy would be that engineering intelligence, it's not about just breaking apart systems and putting them back together in the right way. It's this coarser disambiguation of core phenomena from peripheral phenomena. And it's this disambiguation that ultimately is dissolving the system boundaries, and really respects this crucial role of this dynamic entanglement, if you will, that occurs between AI and their environments. So that leads to the final takeaway of this tutorial, which is that this core and periphery are alternative closed system precepts for engineering intelligence that does address in some ways the limitations of current dogma. Essentially, when we're talking about engineering of the core, the testing of the core, we're talking about open systems engineering. Those are the things we can actually functionally break down to parts. We're talking about the periphery, though, we can't. And so naturally, the core and periphery is encompassing. It includes the open systems engineering, as it should, right? Because closed systems is a special case of the open systems. But also, it expands it. So we can consider this sort of dynamic dependencies with the environment and so forth as being within the scope of discourse. So in summary, there are limitations, okay, that we have in our current ways of doing engineering that emerge mostly as intelligence scales, mostly as it's forced to deal with complexity in the environment that it can't deal with by itself. The takeaways were acknowledging this difference between open systems and closed systems, the importance of outcomes, and the difference between focusing on outcomes, outputs and outcomes. And then this idea that these system boundaries dissolve over time as a necessary kind of mechanism. As the comment earlier in psychology or in biology would say it's for survival. As an engineer would say, to make the stakeholder happy, to keep performance up. Lastly, we underscored how this is a different perspective and is an alternative to what I'll call the current dogma. It's not that people aren't, Agile is already doing this kind of thing. DevOps in a sense is doing this kind of thing, continuous improvement, continuous development. But the reason why is that different than what we've done before and why should it be supported, I think is better answered after looking at some general systems theory. So to round out the tutorial, just in summary, we were talking about really this systems and test engineering perspective, okay, which there's a big gap in the conversations on this stuff, and it's important conversations to have. We we looked at a lot of different levels. We first looked at those tractable things, like what can we do today to test the systems we already have? Then we looked at the mathematical structure of learning systems and how that can support engineering activities. And finally, in this most recent lecture, we sort of poked holes in all of that by saying, well, that really applies in the core, but actually there's a much broader scope that we need to consider. In summary, trying to drive to something like a roadmap, like when will this start mattering? I think that's important to answer. And I can't answer it clearly, obviously, but right now, I'd say today, the current state, the normative scenario is this open systems only world, okay? We basically just can define and characterize these learning systems, can define it as a component, okay? Intelligence, is a component, or the learning part is a component. And essentially, this is like the offline AI, where most of the behavior is learned by training offline somewhere. Maybe there's some tweaks online, but not much. In this case, there's not that adaptation over time, really, in a deep sense. As we move towards online kind of settings, though, okay, then I think these edge cases start to creep in. Okay, now, one of the earliest might be the kind of self-destructive AI I talked about earlier, but also other things, just like if reinforcement learning is allowed to learn online and so forth, I think we can interpret some of the things like reward hacking and other things as failures in closed systems engineering. However, I still think those will be largely open systems dominant. Similar to our conversation before regarding this idea of a phase change between the point when we can measure intelligence as like how many tasks can you complete versus actually now it can generate its own tasks and complete its own tasks. I think there's also going to be a phase change where we have to move from a largely open systems dominant, largely systems engineering V, decompose, recompose world to a largely core and periphery top-down management of outcomes of an intelligence system. I don't know when that will be, but as I say, I think it's with the scale of intelligence, like elaborated earlier. So that rounds out the content for this tutorial, and I'd like to open the floor to remaining questions and answers and some discussions.
Some special case of the way the systems have a notion of simulation, and then we could have this continuation between the complexity environment and people, because we can run any algorithm on the machine, and the complexity of these algorithms have a like upper bound limit of certain dynamics, how much energy can spend the computation. And in some way, this exception to this speculation somehow defines the ability of intelligent systems to evolve. Because now upper bound limit of complexity does not match complexity of
Great. Great comment and question. The idea was looking at this slide, talking about transducing complexity, that a Turing complete intelligent component has the ability to represent as much complexity, basically infinite level of complexity in theory, and then in practice, it's just bounded by, say, the time and resource cost to run those computations. Well, first, I think that so there's an upper bound, and so then the question is, well, if there's this upper bound, then how does it survive if it has to deal with all this complexity and so on and so forth? So is this a special case where it maybe doesn't need all of this or something like that, but just generally on the idea? So I think that's a great point. And one thing though is that there's the complexity of the internal representations, and then there's the complexity of the actions that a system can take in the real world. So if something's Turing complete, but it has no outputs, then it can't affect the outcomes necessarily, or it won't know it's affecting the outcomes or something. Like it can't actually actuate itself. So there is a difference between the complexity of the action space and the complexity of sort of internal representations and so forth. But leaving that aside, I think that actually this still stands fine, because what's going on is with the constraint, it's basically a time constraint you're adding, that Turing complete in like given enough time and resources could represent anything, but it certainly can't. Now, as far as how these systems actually survive in the world when there's so much complexity, I think there's this nuanced point which sounds philosophical, but then becomes very real, which is kind of like the environment isn't literally the environment. It's the sort of subjective experience of the environment that matters. And it's also subjective to the tasks and et cetera that are being done. So, so one example of basic intelligence, sometimes people say, like, if you lift up a log, you'll see all these like bugs running around. And why are they running around? And it's an example of intelligence as the minimization of state dynamics, because basically they just want to get in the dark again, right? So they're just hunting for a dark place. How do they see, right? The environment's so complex and going on. So this is actually kind of an argument for why there are ecological niches in the environment. Each little intelligence has its own little thing to do, way it survives and the way it constrains the way it perceives the world. On the other hand, it might be the case that we're just thinking about this backwards, because we're kind of like, I've taken this engineering perspective, like we're building this thing and it's going to be intelligent and go create all these changes. But on the other hand, in a very abstract way, nature itself is the best, is the best engineer of intelligent systems, because somehow it orchestrates all of us to interact together and to do things, et cetera, and to be intelligent in a way. I mean, not that it's trying to do that, but the point is, the environment sort of sets a tone or frequency that all the intelligent systems have to conform to. And people have spoken about this even at this conference in years past, that that it might actually be a kind of resonance with the environment, and the environment's kind of orchestrating other systems together in order to well, it's not necessarily doing it in order to, what I'm trying to say is that the survival of individual systems within a grander environment might be its ability to navigate the various frequencies of the environment, as opposed to a top-down, like how do we control it to do what we want it to do. So more like a judo kind of thing, right? It's, the environment's moving this way, so we can step in and make some kind of change. We can't necessarily stand in front of this big wave and force it to stop. So very interesting idea. Is there any other comments, questions? The question is, what do we mean by scale here? And it does have to do with like the number of components or, yeah. Here I'm talking about the scale of intelligence. And remember before I said I wasn't going to define intelligence, right? No, and here I'm referring it to the scale in the ability to create the complexity in order to regulate the outcomes. So I've sort of said, okay, we're scaling intelligence by scaling the complexity of the outputs that the intelligence system is able to produce, which is maybe a very crude concept, right? But we can define it with just set theory, as opposed to more complex things like adaptation under constraints. Well, what's adaptation? What are the constraints, and so forth? So it's not scale like in cleverness or IQ, but rather just the capacity to handle complexity. That's what I mean here. Yeah, so the comments about measurability. So I purposely started with the practical lecture and worked more and more philosophical as I went. There was a question at the end of the last session about what are the future directions for research, and I think a lot of it is around this. Is that it's a compelling intellectual idea. I've built it up from scratch with systems theory, but of course it's inspired by the psychology and the biology and the other things. There's some kind of fundamental truth to it. So how do we measure this stuff? First question is, how do you scope the system? Didn't I just say we can't scope the system? How do you get core and periphery if you can't scope the system? We have to expand what we think closure is. In many ways, when people talk about a closed system, they say, oh, it's a system without inputs or outputs. In which case, it kind of is the universe, right? I mean, how would you say, okay, this system has outputs, but something's giving it its inputs. And then that one, something's giving it its inputs, and so on and so forth. So is there really any boundary you can draw, even if you say functionally? Probably not. So then there's a concept of functional closure, maybe, that something is closed because it's stable in the sense of like, okay, if we give it any additional inputs, the function isn't changing, something like that. So there's a kind of functional closure that might be useful, but that also sort of falls down because how often is that true? And also it's still rooted in functions. I think we have to go to information and build some kind of information closure. And the rough idea there is something like, if we can define or scope what information is relevant at a given point in time, then we can sort of scope the broader context around the system that's relevant. That gives us our environment. And then within that, we still have our original system defined the normal way. So when I talk about comparing the core and periphery of the system and environment, if we can scope the closed system using information, maybe that's a start. So a simple example of that would be like merging on the highway, right? You're driving down the on-ramp, nothing matters, really, it's just you and the road, maybe someone in front of you. But then when you go to merge, all of a sudden there's like 3 or 4 other cars around you that are crucial to whether or not you can appear intelligent as a driver trying to merge onto the highway. So it's dynamic, right? And so I don't think it's functional. I don't think it's set theoretic. I think it's informational. So what's relevant at a given point in time. Now, once you have that, how you measure the complexity, I don't know. I mean, they're talking about Shannon entropy, but I don't know how meaningful necessarily that is. So you have to build up to it. But at least looking internally at the intelligence system, I think Shannon entropy or basic other measures can tell us what's changing or not. And then that can help direct our focus on engineering side, at least, of like what kind of tests should we be using, or earlier I said like, okay, the environment's really changing, but the system's not changing. So the environment is very periphery and the system is very core. Is that a problem? Like maybe, and maybe that's a huge problem. So those kind of simple things I think we could measure. And it's sort of like a checklist of what's the general regime we're operating in. but it doesn't really give us a good optimization, measure like for formulating that. Very interesting comment. So the comment was, we could think about measurement in terms of what's the theoretical limit of how much the complexity, basically the information in the environment versus how much it's producing at a given point in time. And that gives a sense of how intelligent it is relative to an upper bound. I think that's a great point, especially thinking overall. And how do you model the system so you can calculate information and so forth? Maybe that's something we can't easily say at this pure mathematical level. So the question was on the relationship of intelligence and compression. And so we're at this point in the tutorial. So let me try to answer in the context of the things I've been discussing. I guess the question there is, there's a kind of philosophy like, when you know something really well, you can say it simply, something like that, right? I think maybe that's like having the minimal complexity required to create the outcome you want, and being able to like ride that line over time, where you're not having to overexert yourself. To me, that could be a sign of intelligence, as opposed to like, you're just like this brutally intelligent thing with no finesse. However, if we define intelligence, like here, we're kind of talking about managing the complexity of outcomes, it's not compatible with that, right? So, I don't know what to say. I think, yeah, this actually reminds me of the DNA conversation too, right? Because so much is compressed into our DNA, but it seems like the more that's compressed, the less it can change, in a sense. Like if our DNA changes at all, it's a big problem usually, right? Not always, but usually. And so I think this is another thing, that the more compressed the intelligence is an individual component, the more that individual component has to be buffered from the environmental changes. Okay, as opposed to more distributed intelligence, you could lose, you can lose some neurons and still be fine or something. But if one neuron is doing all the work, it's dangerous. Maybe it's very intelligent, but it loses some other system property like reliability or something like that. Any other interesting, like I'm happy just to talk about things up here, but any other interesting questions or non-interesting questions? The question is basically what modeling language should we use for this? So the question was domain specific language. I think domain specific languages in computer science are a very specific thing, but I will say that there's this thing called SysML, the systems modeling language, which in the past was a certain XML schema basically for how to represent systems and so forth. But moving forward, they're going to release a new version of that. That's it's a kind of unified modeling language, but now they want to move beyond that to something more capable. So it's a technical answer, but yeah, there is something called SysML, which people use to model systems components. And right now I am working on that with that learning system and basic examples. So like take the UAV, can we model that with SysML? And then can we plug that in and generate test requirements and so forth automatically, just as we do for sensor systems and so forth. There's another modeling language. This one is really esoteric, but it's called ATML, Automated Test Markup Language. It's an IEEE standard 1671, I believe. And it was designed for automated test in general, but mostly for like, you can think of it as like building like really good voltmeters. Like you can plug it into a computer and test all the connections and even can send some basic signals through and make sure that they're processed the way it should be. But I think that language is a little bit limited for thinking about tests for AI, exactly because we have to sort of be modeling what the operating envelope is over time and then assessing like localizing how close are we to the border of our capabilities and so forth. So it's not really just like a, hey, send electrical signal through and we'll know if it's good or not. So regarding modeling the system, I think SysML, SysML 2.0 would be the standard to fit with. Regarding modeling the tests, I think that's a very open question. Yes, sir. Yeah, so the question was, will a system be able to design its own experiments and tests to test itself, to test its environment? I think it's absolutely. And you're setting me up to just sort of give my philosophy on this kind of thing of where it's headed. And I mentioned earlier this idea of digital engineering, but the idea of the engineering process becoming more automated and more model based would facilitate that kind of thing. So basically, once in the vision of digital engineering is we have some combination of formal models, which are suitable for formal methods, and maybe some other things that can be processed with like natural language processing or something like that, like paper documents and so forth. And that then top down, we can reason about how things should be or how things are within the system and look at configurations. Regarding testing the environment, I think that is, I mean, I've been talking about top-down engineering. If it's the intelligent system over time, it's not like a stakeholders come and said, hey, build me this thing, and then I'm building an intelligent system. And then it happens to be able to do engineering itself. In that kind of story, then I think testing the environment should be a learned behavior that it just knows, hey, my success is dependent on the environment, my survival, that sort of boundary maybe between biological or natural kind of systems. Often it's a lot of times the arguments are driven by survival, why it does what it does. And we don't necessarily have that for engineered systems. There was one more thing in my mind. Oh yeah. There's this idea out there. You might have seen this picture. I wish I should have had it in a backup slide, but it's like an iceberg. And on top of the iceberg, it says like algorithms or AI or something. And on the bottom of the iceberg is just like cloud centers, distributed computing. And it's that we've sort of had the same algorithms for 50 years or something like that with slight improvements. And the main change is the access to compute over time. And I think that has been the story as a powerful image, I think, for people and explanatory, even if it's a bit defamatory to machine learning researchers. However, I think moving forward, a better picture is something like the AI and autonomy and even the human systems that are teaming with those things are above the waterline, okay, above the iceberg. And beneath that is still distributed computing, but beneath distributed computing is something like digital engineering, enhanced with formal methods and theorem proving and all these other kinds of intelligence that is sort of the framework which guides what we should be using that distributed computing for. Okay, so for example, you might have a bunch of unmanned aerial systems out there flying around, and you also need to be checking, is it within regulatory compliance? Is it, is there some safety properties, like it's not going to hit a wall or whatever? Those are all tests that actually can be driven from way deep within the system, from some sort of digital engineering intelligence saying, hey, look, run the computations and maybe even at the edge for this thing because it's now in a new regulatory regime. That's all to say that, and I kind of alluded to this earlier, is there's this sort of surface, almost superficial level AI that we'll see and interact with on a day-to-day basis. But then there's a question of what's maybe the more artificial general intelligence underlying the whole thing that's playing this more orchestration role. What I've just described was shown in a movie. It's called like Skynet or something like that. But in these different visions for what intelligence is, one of them is basically really good backend for digital engineering, which is controlling everything else to meet this level of complexity. So that's one of the things that keeps me in this research area is to engineer those things right. Okay, don't give them too many bad ideas. Any other questions or food for discussion? Okay, well, this has been great. Thank you. I really appreciate everybody attending and talking. Thank you very much. Yeah, so, oh, one last thing. There's my personal information if you ever want to reach out or talk about this kind of stuff. Email is probably the best form to get to me. And I'll be on this problem for the foreseeable future. So if it ever comes up in your life, you know, you can call me. Not like bat signal level, but, you know, at least have a conversation or something. So, okay, thank you again.